All right. All right, all right, all right. Let's see here. What is... What? What? Okay. Let's see. Yeah. Okay. Um, there you go. Fine. What? 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 Huh? Keeps getting in and then dying. Why? Why? Uh, uh, it's not that. What? What? Hello? What is he? Ah, oh well, he can figure it out on his own. Ah. Attention, here be dragons. This is the latest unstable version of documentation, which made document features not available or compatible with release stable versions of Godot. See the stable versions of this documentation page instead. I'd say, what version am I using for Godot? What version? 4.3. Alright, let's go to the 4.3 documentation. Documentation changelog. 4.3. Talks. Okay. Godot's documentation is available in various languages and versions. Expand the Read Docs panel at the bottom of the sidebar to see the list. Well, we don't need to see it in various languages. All we need to see it in is in English. Because English. Yeah. Welcome to the official documentation of Godot Engine, the free and open source community-driven 2D and 3D game engine. If you are new to this documentation, we recommend that you read the introduction page to get an overview of what this documentation has to offer. To begin reading the relevant documentation, select the tile that matches your profile. I've never made a game before, and I want to make a game. I know how to make a game. I want to know how to use Godot. I know how to use Godot. I want to learn more advanced Godot topics. I know how to use Godot. I want to contribute to Godot. Well, let's see. You can also use a stable. Hey,
Balls.
what? Why'd you keep on dying?
It was intentional.
It was okay, okay, okay. Was it like every time I spoke or something, or was it just like, oh, 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 oh,
Because it
oh,
was funny.
oh? Okay, okay. First save actually
I'm
learning
also
Godot.
doing things.
Oh, what you doing?
Changing thumbnails.
Ah, ah. So how the hell did you forget about making the thumbnail?
Because
I,
I didn't. I
yeah,
was asleep.
no, you made it. You made it. It exists. You just
That man made it.
you just you just forgot in a tired stupor.
No, I straight up did not do that shit. I was asleep by the time that shit was uploaded.
Then who the hell did that?
I don't know.
You, it wouldn't have been your brother or your mother or Binks or
You're
the
right.
other cat.
No, it was obviously the cats.
Ah, yeah, yeah, yeah. They can read
Hence
your
why shit
mind.
like fucking Baboon Lagoon was typed.
Baboon Lagoon. Six.
Approximately 12 minutes after I died.
Aw. I have no idea how. I, so you did it. You just don't remember. Yeah.
No, I know for a fact I was laying down in bed and died by that time.
And then you woke up and then fell back asleep soon after.
I did not wake up.
Prob.
I would remember doing that.
Are you sure?
Pretty sure.
Because my sister forgets that she's woken up sometimes.
Yeah, but that's her, not me.
Well, it's just an example. It's not impossible.
I'm aware, but it's not what I do. I
Uh-huh.
don't do that.
Uh-huh. It's not exactly like a mental condition, Ethan. Anybody can experience it.
I'm well aware.
All right, let's read this documentation, shall we?
Nah, fuck around and find out on your own. Don't read any instructions.
But then I don't know what shit does. All right.
Precisely. That's how
Godot
you figure it out
Engine.
yourself.
Godot Engine is an open source project developed by a community of volunteers. The documentation team can always use your feedback and help to improve the tutorials and class reference. If you don't understand something or cannot find what you are looking for in the docs, help us make the documentation better by letting us know. Submit an issue or pull request on the GitHub repository, help us translate the documentation into your language, or talk to us on the hashtag documentation channel on the Godot contributors chat. Offline documentation. To browse documentation offline, you can download the HTML copy, updated every Monday, stable latest 3.6. Extract the zip archive, then open the top-level index.html in a web browser. For mobile devices or e-readers, you can also download the EPUB copy, updated every Monday, stable latest 3.6. Extract the zip archive, then open the Godot engine.epub file in an ebook reader application. Alright, and in case there's any information that I don't know, I'm going to click on the I've never made a game before, I want to make a game. Alright, introduction. GD script, C#. Welcome to the official documentation of Godot Engine, the free and open source community-driven 2D and 3D game engine. Behind this mouthful, you'll find a powerful yet user-friendly tool that you can use to develop any kind of game for any platform with no usage restriction whatsoever. This page gives a broad overview of the engine and of its documentation, so that you know where to start if you are a beginner or where to look if you need information on a specific feature. Before you start, the tutorials and resources page lists video tutorials contributed by the community. If you prefer video text, consider checking them out. Otherwise, getting started is a great starting point. In case you have trouble with one of the tutorials or your project, you can find help on the various community channels, especially the Godot Discord community forum, and community Discord community and forum. Bleh. About Godot Engine, a game engine is a complex tool and difficult to present in few words. Here's a quick synopsis, which you are free to reuse if you need a quick write-up about Godot Engine. Godot Engine is a feature-packed cross-platform game engine to create 2D and 3D games from a unified interface. It provides a comprehensive set of common tools so that users can focus on making games without having to reinvent the wheel. Games can be exported with one click to a number of platforms, including the major desktop platforms Linux, Mac OS, Windows, mobile platforms, Android, iOS, as well as web-based platforms and consoles. Godot is completely free and open source under the permissive MIT license. No strings attached, no royalties, nothing. Users' games are theirs, down to the last line of engine code. Godot's development is fully independent and community-driven, empowering users to help shape their engine to match their expectations. It is supported by the Godot Foundation, not for profit. Yay, good engine. Organization of the documentation. This documentation is organized into several sections. About contains the introduction as well as information about the engine, its history, its licensing, authors, etc. It also contains the frequently asked questions. Getting started contains all necessary information on using the engine to make games. It starts with the introduction section, which should be the entry point for all new users. This is the best place to start if you're new. The manual can be read or referenced as needed in any order. It contains features, specific tutorials, and documentation. Engine details contains sections intended for advanced users and contributors, with information on compiling the engine, working on the editor, or developing C++ modules. Community is dedicated to the life of Godot's community and contains a list of recommended third-party tutorials and materials outside of this documentation. It also provides details on the asset library. It also used to list Godot communities, which are now listed on the Godot website. Finally, the class reference documents the full Godot API, also available directly within the engine's script editor. You can find information on all classes, functions, signals, and so on here. In addition to this documentation, you may also want to take a look at the various Godot demo projects. About this documentation, members of the Godot engine community continuously write, correct, edit, and improve this documentation. We are always looking for more help. You can also contribute by opening GitHub issues or translating the documentation into your language. If you are interested in helping, see how to contribute in writing documentation, or get in touch with the documentation team on Godot contributors chat. All documentation content is licensed under the permissive Creative Commons Attribution 3.0. License with attribution to Juan Lenetsky, Ariel Manzur, and the Godot engine community, unless otherwise noted. Have fun and make games with Godot engine. Huzzah! Onto the lit. Ah, damn. Unfortunate. Ah, that makes sense though. Don't worry about what I'm doing. I'm not doing anything nefarious. List of features. This page aims to list all features currently supported by Godot. Let's see. Introduction. Okay. This page lists features supported by the current stable version of Godot. Some of these features are not available in the 3.x release series. Platforms. Also see system requirements for hardware and software version requirements. For information about console support, see the Godot website. Can run both the editor and exported projects, Windows, x86, and ARM, 64-bit and 32-bit. Don't need to worry about the others because we will not be using them. Linux supports RV64, RISC-V, runs exported projects, iOS. Godot aims to be all as platform independent as possible and can be ported to new platforms with relative ease. Projects written in C# using Godot 4 currently cannot be exported to the web platform. To use C# on that platform, consider Godot 3 instead. Android and iOS platform support is available as of Godot 4.2, but is experimental and some limitations apply. Editor features. Scene Tree Editor, built-in script editor, support for external script editors such as Visual Studio Code or Vim. GDScript Debugger. Support for debugging in threads is available since 4.2. Visual Profiler with CPU and GPU time indications for each step of the rendering pipeline. Performance monitoring tools including custom performance monitors, live script reloading, live scene editing. Changes will reflect in the editor and will be kept after closing the running project. Remote Inspector. Changes won't reflect in the editor and won't be kept after closing the running project. Live camera replication. Move the in-editor camera and see the result in the running project. Built-in offline class reference documentation. Use the editor in dozens of languages contributed by the community. Plugins. Editor plugins can be downloaded from the asset library to extend editor functionality. Create your own plugins using GDScript to add new features or speed up your workflow. Download projects from the asset library and the project manager and import them directly. Ugh. My nose. Ugh. Stuffy. Rendering. Godot 4 includes 3 renderers. Forward Plus, the most advanced renderer suited for desktop platforms only. Used by default on desktop platforms, the renderer uses Vulkan, Direct3D, 12, or Metal as the rendering driver, and it uses the rendering device backend. Mobile, fewer features, but renders simple scenes faster, suited for mobile and desktop platforms. Used by default on mobile platforms, this renderer uses Vulkan, Direct3D, 12, or Metal as the rendering driver, and it uses the rendering device backend. Compatibility, sometimes called GL compatibility, the least advanced renderer suited for low-end and desktop and mobile platforms. Used by default on the web platform, this renderer uses OpenGL as the rendering driver. See overview of renderers for a detailed comparison of the rendering methods. 2D graphics, sprite, polygon, and line rendering. High-level tools to draw lines and polygons such as Polygon 2D and Line 2D will support for texturing. Let's see, I have Godot pulled up, so we can just switch over here. Let's see. What was it? Oh, wait. 2D graphics. Sprite, polygon, and line rendering. Okay. Sprite, polygon, line. Let's take a look at Sprite. Hello, Sprite. Then script editor. 2D graphics. Animated Sprite 2D as a helper for creating animated sprites, parallax layers, pseudo 3D support, including preview in the editor. 2D lighting with normal maps and specular maps, point, omnispot, and directional 2D lights. Hard or soft shadows adjustable on per light basis. Custom shaders can access real-time SDF representation of the 2D scene based on light ocular 2D nodes, which can be used for improved 2D lighting effects, including 2D global illumination. Font rendering using bitmaps, rasterization using free type or multi-channel sign distance fields, MSDF. Bitmap fonts can be exported using tools like BMF font or imported from images for fixed width fonts only. Dynamic fonts support monochrome fonts as well as colored fonts, e.g. for example for emoji. Supported formats are TTF, OTF, WOFF1, and WOFF2. Dynamic fonts supports optional font outlines with adjustable width and color. Dynamic fonts support variable fonts and open type features, including Ligatures. Dynamic fonts support simulated bold and italic when the font file lacks those styles. Dynamic fonts support oversampling to keep fonts sharp at higher resolutions. Dynamic fonts supports subpixel positioning to make fonts crisper at lower sizes. Dynamic fonts supports LCD subpixel optimizations to make fonts even crisper at low sizes. Ugh. Ugh. Signed distance field fonts can be scaled at any resolution without requiring re-rasterization. Multi-channel usage makes SDF fonts scale down to lower sizes better compared to monochrome SDF fonts. GPU-based particles with support for custom particle shaders. CPU-based particles, optional 2D HDR rendering for better glow capabilities. 2D tools, tile maps for 2D tile-based level design. 2D camera with built-in smoothing and drag margins. Path 2D node to represent a path in 2D space. Can be drawn in the editor or generated procedurally. Path follow 2D node to make nodes follow a path 2D. Alright. Yeah. 2D geometry helper class. What does that do? Hey, hey, Godot. Hey, Godot engine documentation. What does that do? 2D physics. Physics bodies, static bodies, animated bodies for objects moving only by script or animation such as doors and platforms. Rigid bodies, character bodies, joints, areas to detect bodies entering or leaving. Collision detection, built-in shapes, line, box, circle, capsule, world boundary, infinite plane. Collision polygons can be drawn manually or generated from a sprite in the editor. 3D graphics, HDR rendering with sRGB. Perspective, orthographic, and frustum offset cameras. When using the forward plus rendering, a depth prepass is used to improve performance in complex scenes by reducing the cost of overdraw. Variable rate shading on supported GPUs in forward plus and mobile. Physically based rendering, built-in material features. Follows the Disney PBR model, supports Burley, Lambert, Lambert Wrap, Half Lambert, and Toon Diffuse shading modes. Supports Schlick GGX tune and disabled specular shading modes. Uses a roughness metallic workflow with support for ORM textures. Uses Horizon specular occlusion filament model to improve material appearance. Normal mapping, parallax relief mapping with automatic level of detail based on distance. Detail mapping for the albedo and normal maps, subsurface scattering and transmittance. Screen space refraction with support for material roughness, resulting in blurry refraction. Proximity fade, soft particles, and distance fade. Distance fade can use alpha blending or dithering to avoid going through the transparent pipeline. Dithering can be determined on a per pixel or per object basis. Real-time lighting. Directional lights, sun, moon, up to 4 per scene. Omnidirectional lights, spotlights with adjustable cone angle and attenuation. Specular, indirect light, and volumetric fog energy can be adjusted on a per light basis. Adjustable light size for fake area lights will also make shadows blurrier. Optional distance fade system to fade distant lights and their shadows, improving performance when using the forward plus renderer. Default on desktop. Lights are rendered with clustered forward optimizations to decrease their individual cost. Clustered rendering also lifts any limits on the number of lights that can be used on a mesh. When using the mobile renderer, up to 8 Omni lights and 8 spotlights can be displayed per mesh resource. Baked lighting can be used to overcome this limit if needed. Shadow mapping, directional light orthogonal, fastest, PSSM 2 split and 4 split, supports blending between splits. OmniLight, dual paraboloid, fast or cube map, slower but more accurate, supports colored projector textures in the form of panoramas. Spotlight, single texture, supports colored projector textures. Shadow, normal offset bias, and shadow pancaking to decrease the amount of visible shadow acne, and Peter panning. PCSS, like shadow blur based on the light size and distance from the surface the shadow is cast on. Adjustable shadow blur on a per light basis. Global illumination with indirect lighting. Baked light maps, fast but can't be updated at runtime. Supports baking indirect light only or baking both direct and indirect lighting. The bake mode can be adjusted on a per light basis to allow for hybrid light baking setups. Supports light dynamic objects using automatic and manual placed probes. Optionally supports directional lighting and roughness reflections based on spherical harmonics. Light maps are baked on the GPU using compute shaders, much faster compared to CPU light mapping. Baking can only be performed from the editor, not in exported projects. Supports GPU-based denoising with JNLM, or CPU/GPU-based denoising with OIDN. Voxel-based GI probe supports dynamic lights and dynamic occluders, while also supporting reflections. Requires a fast baking setup which can be performed in the editor or at runtime, including from an exported project. Signed Distance Field GI, designed for large open worlds, supports dynamic lights but not dynamic occluders, supports reflections, no baking required. Screen space, indirect lighting, SSIL, or at half or full resolution, fully real-time, and supports any kind of emissive light source, including decals. Voxel GI and SDF GI use a deferred pass to allow for rendering GI at half resolution to improve performance, while still having functional MSAA support. Reflections, voxel-based reflections when using GI probes, and SDF-based reflections when using signed distance field GI. Voxel-based reflections are visible on transparent surfaces, while rough SDF-based reflections are visible on transparent surfaces. Fast-baked reflections or slow real-time reflections using reflection probe parallax box correction can optionally be enabled. Screen space reflections with support for material roughness reflection techniques can be mixed together for greater accuracy or scalability. When using the forward plus renderer default on desktop, reflection probes are rendered with the clustered forward optimizations to decrease their individual costs. Clustered rendering also lifts any limits on the number of reflection probes that can be used on a mesh. When using the mobile render, up to 8 reflection probes can be displayed per mesh resource. When using the compatibility renderer, up to 2 reflection probes can be displayed per mesh resource. Give me a second. I want to... Hmm. Never mind. Don't mind me. I'm just doing things. And the things that I am doing is trying to see if I can move the chat to the other side of Streamlabs so that I can more easily pay attention to it. But no, I cannot do that, apparently. Maybe it wasn't the best idea to pick up a piece of gum. Well, what I should do is take my Adderall. That's definitely a thing I should do. Don't forget, water. Alright. Decals. Supports albedo, emissive ORM, and normal mapping. Texture channels are smoothly overlaid on top of the underlying material with support for normal ORM only decals. Yeah. Definitely should not have picked up that piece of gum. Oh well. Oh well. Just stick it up there for now. Support for normal fade to fade decal, depending on its incidence angle, does not rely on runtime mesh generation. This means decals can be used on complex skinned meshes with no performance penalty, even if the decal moves every frame. Supports for nearest bilinear, trilinear, or anisotropic texture filtering configured globally. Optional distance fade system to fade distance decals, improving performance. When using the forward plus render, default on desktop, decals are rendered with the clustered forward optimizations to decrease their individual cost. Clustered rendering also lifts any limits on the number of decals that can be used on a mesh. When using the mobile renderer, up to 8 decals can be displayed per mesh resource. Sky, panorama sky using HDRI. Wait. Let me see. This is all under 3D graphics. I'm not going to be using 3D graphics, so I can just skip past all this. 3D tools, 3D physics. Shaders. 2D, custom vertex, fragment, and light shaders. Text-based shaders using shader language inspired by GLSL. Visual shader editor, support for visual shader plugins. Scripting. Yay. General, object-oriented design pattern with scripts extending nodes, signals and groups for communicating between scripts, support for cross-language scripting, many 2D, 3D, and 4D linear algebra data types such as vectors and transforms. GDScript, high-level interpreted language with optical static typing. Syntax inspired by Python, however GDScript is not based on Python. Syntax highlighting is provided on GitHub. Use threads to perform asynchronous actions or make use of multiple processor cores. C#. Packaged in a separate binary to keep files and dependencies down, supports .NET 8 and higher. Full support for C# 12.0 syntax and features. Supports Windows, Linux, and macOS since Godot 4.2. Experimental support for Android and iOS is also available. On the iOS platform, only some architectures are supported. ARM64. The web platform is currently unsupported. To use C# on that platform, consider Godot 3 instead. Using an external editor is recommended to benefit from IDE functionality. GD extension, C, C++, Rust, D, etc. When you need it, link to native libraries for higher performance and third-party integrations. For scripting, GameLogic, GDScript, or C# are recommended if their performance is suitable. Official GD extension bindings for C and C++. Use any build system and language features you wish. Actively developed GD extension bindings for D, Swift, and Rust. Bindings and Rust bindings provided by the community. Some of these bindings may be experimental and not production ready. Audio features mono, stereo 5.1 and 7.1 output. Non-positional and positional playback in 2D and 3D. Optional Doppler effect in 2D and 3D. Support for rewritable audio buses and effects with dozens of effects included. Support for polyphony. Playing several sounds from a single audio stream player node. Support for random volume and pitch. Support for real-time pitch scaling. Support for sequential random sampling selection, including repetition prevention when using random sample selection, listener 2D and listener 3D nodes to listen from a position different than the camera. Support for procedural audio generation, audio input to record microphones, text-to-speech using platforms provided TTS engines, MIDI input, no support for MIDI output yet. Aw, sad. APIs used, Windows, WASAPI. Okay, cool. Don't need to know anything else. Import, support for custom import plugins, formats. Images, see imported images, audio. WAV and optional IMA, ADPCM, compression, OGG, Vorbis, MP3, 3D scenes, see imported 3D scenes, support for loaded GLTF 2.0 scenes at runtime, including the exported project. Input mapping system using hardcore inputs, events, or remapping. Okay. Legitimately, I think we can skip all this. And all this. Probably this. If I have any questions, I'll definitely go back to that. Complying with the license. I think we should be fine. Documentation changelog, don't need to worry about this. Alright. Ooh, that looks cool. I wonder what games these all are. I should probably read this. Introduction to Godot. This article is here to help you figure out whether Godot might be a good fit for you. We will introduce some broad features of the engine to give you a feel for what you can achieve with it, and answer questions such as what do I need to know what what do I need to know how to get started. Blech. This is by no means an exhaustive overview. We will introduce many more features in this Getting Started series. What is Godot? Godot is a general-purpose 2D and 3D game engine designed to support all sorts of projects. You can use it to create games or applications you can then release on desktop or mobile, as well as on the web. You can also create console games with it, although you either need strong programming skills or a developer to port the game for you. I might need that. What can the engine do? Godot was initially developed in-house by the Argentinian game studio. Its development started in 2001, and the engine was... Where...
Balls.
Where'd you... Well, come on, come back. Or is that all he's gonna do? Is he just gonna come back and say balls? Undeafen himself and just say balls? Is that it? I think that might be it. Okay, back to it. Some examples of games created with Godot include Cassette Beast, PVKK, and Usagi Shima. As for applications, the open source pixel art drawing program Pixelorama is powered by Godot, and so is the voxel RPG creator RPG in a Box. You can find many more examples in the official showcase. Games. Slay the Spire 2. Oh. Organized Inside, Spooky Express, Bricks Breaker RPG, Rift Drift. I don't... Canado Pet. Oh. Buckshot Roulette. Nice. Window Kill. I know that one. Endoparasitic. Really? Brotato. Damn, this is quite the selection. Apps and tools. Zogot. Godot for iPad and iPhone. Paragraphic. Action Game Maker. Pixelorama. What is this? Oh. Ah, okay. I might want to pick that up. These are some really nice games here. Yeah, great game. How does it work and look? Godot comes with fully fledged game editor integrating tools to answer the most common needs. It includes a code editor, an animation editor, a tile map editor, a shader editor, a debugger, a profiler, and more. The team strives to offer a feature-rich game editor with a consistent user experience. While there's always room for improvement, the user interface keeps getting refined. Of course, you never want to not have it be getting refined, you know? Of course, if you prefer, you can work with external programs. We officially support importing 3D scenes designed in Blender and maintain plugins to code in VS Code and Emacs for GDScript and C Sharp. We also support Visual Studio for C Sharp on Windows. Alright. Well, I have Blender, so I don't need a... But I won't be making 3D assets. Maybe. Unless I were to do something like Tenna from Deltarune Chapter 3. Programming languages. Let's talk about the available programming languages. You can code your games using GDScript and Godot-specific and tightly integrated languages with a lightweight syntax, or C Sharp, which is popular in the games industry. These are two main scripting languages we support. With the GD extension technology, you can also write gameplay or high-performance algorithms in C++ or other languages without recompiling the engine. You can use this technology to integrate third-party libraries and other software development kits, SDK, in the engine. Of course, you can also directly add modules and features to the engine, as it's completely free and open source. What do I need to know to use Godot? Godot is a feature-packed game engine with thousands of features. There is a lot to learn. To make the most of it, you need programming foundations. Good programming foundations. While we try to make the game accessible, you will benefit a lot from knowing how to think like a programmer first. I already know that. Godot relies on the object-oriented programming paradigm. Being comfortable with the concepts such as classes and objects will help you code efficiently in it. If you are entirely new to programming, GD Quest Learn GDScript from Zero is a free and open source interactive tutorial for absolute beginners to learn to program with Godot's GDScript language. It is available as a desktop application or in the browser. We will provide you with more Godot-specific learning resources in learning new features. In the next part, you will get an overview of the engine essential concepts. Huzzah! Next section. Oh god, I'm sore. From what? Beat Saber. In Godot, you can write using the GDScript and C Sharp programming languages. If you are new to programming, we recommend starting with GDScript because we designed it to be simpler than all-purpose languages like C Sharp. It will both be faster and easier to learn. Okay, I've been thinking about it because it keeps mentioning the two, right? Do I want to work in C Sharp or do I want to work in GDScript? It says that it'll be faster and easier to learn. However, C Sharp directs more, or I would assume it talks more directly with the actual computer itself and is thus more efficient. And it is more applicable to a job that I can get outside of this. So we'll see. We'll see. Gotta read through all this first, you know. Blech. While GDScript is a language specific to Godot, the techniques you will learn with it will apply to other programming languages. Yes, I already know that. But I need to learn C Sharp. Because it is a widely used programming language. Note that it is completely normal for a programmer to learn and use multiple languages. Programming languages have more similarities than differences. So once you know one, you can learn another much faster. Learn in your browser with GDScript app. To learn GDScript, you can use the app Learn GDScript from Zero. It is a complete beginner course with the interactive practices you can do right in your browser. Yep. Click here to access Learn GDScript from Zero app. I will take a look at that later. This app is an open source project. To report bugs or contribute, head to the app's source code repository, GitHub repository. In the next part, you will overview. You'll get an overview of the game engine's essential concepts. User contributed notes. All right. Wow. This is a short one. Overview. I'm fine. Mouth liquids. Overview of Godot's key concepts. Every game engine revolves around abstractions you use to build your application. In Godot, a game engine is a tree of nodes that you group together into scenes. You can then wire these nodes so they can communicate with using signals. There are four concepts you will learn here. We are going to look at them briefly to give you a sense of how the engine works. In the Getting Started series, you will get to use them in practice. Scenes. In Godot, you will break down your game in reusable scenes. A scene can be a character, a weapon, a menu in the user interface, a single house, an entire level, or anything you can think of. Godot's scenes are flexible. They fill the role of both prefabs and scenes in some other game engines. Alright. That... Okay. That... Hmm. That should make things convenient and more flexible. You can also nest scenes. For example, you can put your character in a level and drag and drop a scene as a child of it. Alright. Nodes! A scene is composed of one or more nodes. Nodes are your game's small building blocks that you arrange into trees. Here's an example of a character's nodes. Camera 2D, sprite 2D, collision shape 2D. Yay. It is made of character body 2D node named player, a camera 2D, a sprite 2D, and a collision shape 2D. Note, the node names with the 2D end with 2D because this is a 2D scene. Their 3D counterparts have names that end with 3D. Be aware of that spatial nodes are now called Node 3D, starting with Godot 4. Yeah, that makes sense. Notice how nodes and scenes look the same in the editor. When you have a tree of nodes as a scene, it then shows a single node, with its internal structure hidden in the editor. Godot provides an extensive library of base node types you can combine and extend to build more powerful ones, 2D, 3D, or user interface. You'll do most things with these nodes. The scene tree. All your game scenes come together in the scene tree, literally a tree of scenes. As scenes are trees of nodes, the scene of tree is also a tree of nodes. But it's easier to think of your program in terms of scenes, as they can represent characters, weapons, stores, or your user interface. Signals. Nodes emit signals when some event occurs. This feature allows you to make nodes communicate without hardwiring them in code. It gives you a lot of flexibility in how you structure your scenes. Note, signals are Godot's version of the observer pattern. You can read more about it here. Observer pattern. Okay, I don't know what that is. That's still nobody in chat. Unfortunate. For example, buttons emit a signal when pressed. You can connect a piece of code to signal which will run in reaction to this event when starting the game or opening a menu. Other built-in signals can tell you when two objects collide, when a character or monster entered a given area, and much more. You can also define new signals tailored to your game. Summary: nodes, scenes, the scene tree, and signals are four concepts in Godot that you will manipulate all the time. Okay, so I tried messing with Godot before, and I got most everything. except for signals. I didn't know that they existed. Everything else you can see quite plainly, but signals, no. No, you have to do something else, apparently. Nodes are your game's smallest building blocks. You combine them to create scenes that you then combine and nest into the scene tree. You can then use signals to make nodes react to events in other nodes or different scene tree branches. After this short breakdown, you probably have many questions. Bear with us as you get many answers throughout the Getting Started series. First, look at Godot's interface. This page will give you a brief overview of Godot's interface. We're going to look at the different main screens and docks to help you situate yourself. For just speak. It's comprehensive. For a comprehensive breakdown of the editor's interface and how to use it, see the editor manual. I might want to look at that. Okay. The Project Manager. When you launch Godot, the first window you see is the Project Manager. Yep. In the default tab projects, you can manage existing projects, import or create new ones, and more. Oh. At the top of the window, there's another tab named Asset Library. The first time you go to this tab, you'll see a Go Online button for privacy reasons. The Godot Project Manager does not access the internet by default, so to change this, click the Go Online button. You can change this option later in the settings. Once your network mode is set to online, you can search for demo projects in the open source asset library, which includes many projects developed by the community. You know what? Let's check that out. Project Manager. And where? Asset library. Online. Huh. Procedural pixel art tree. Interesting. I might want to take a look at some of these later. Alright. The project manager settings can be opened using the settings menu. Yep. From here you can change the editor's language. Default is the system language, interface theme, display scale, network mode, and also the directory naming convention. To learn the project manager's ins and outs, read using the project manager. First, look at Godot's editor. When you open a new or existing project, the editor's interface appears. Let's look at its main areas. By default, along with the Windows Open Edge, it features Main Menu. On the left, Workspace, switching buttons in the center, Active Workspace is highlighted, and Playtest buttons and the Movie Maker mode to toggle on the right. Yep. And 3D, we don't need that. We're just going to be working in 2D. Is this pixel length? It might be pixel length. Just below the workspace buttons, the open scenes as tabs are seen. The plus button right next to the tab will add a new scene to the project. With the button on the far right, distraction-free mode can be toggled, which maximizes or restores the viewport size by hiding docks in the interface. In the center below the scene selector is the viewport with the toolbar at the top where you'll find different tools. to move, scale, or lock the scene's nodes. Currently, the 3D workspace is active. Hello, what's up?
So close to scary. I was so close to spooking you.
I heard you walk in the door, so I figured you'd be coming my way.
I didn't know if you heard, so I was just, because I just saw you doing that, and I was like, before you even turned, I was thinking, what if I just spooked him? What if I did? Because I did it once. And it was
Yeah?
really funny.
Yeah?
But I never did it again.
You've never done it?
Yeah.
Yeah. Learning Godot.
Learning what?
Godot, the game engine
Oh,
that I'm using.
I've heard of that, but I don't remember much about it.
If you want to hang out with me while I
No.
do it, you can.
No.
Okay. Okay. You want to play my game, which doesn't exist? In the center below the scene editor, the viewport is the toolbar where you'll find different tools to move, scale, or lock the scene's nodes. Currently, 3D workspace is available. The toolbar changes based on the context and selected node. Here is the 2D toolbar. Below is the 3D one. Okay. What all do they got? A lot of
I
different.
have returned.
What the fuck? Don't do that.
Oogly boogly bitch.
Yeah, apparently. Jesus Christ.
I was editing, so I was deafened.
Ah. And now you're no longer editing, so you're no longer deafened.
Because I've just finished getting through the second episode of Game 3.
Yay.
We have 33 minutes of footage from 2 videos.
Why do we keep getting funnier?
You know, that's a really good question.
This is a really bad curse.
And thankfully, though, the next episode is shorter than this one that I just did, so...
Yay. Yay. I haven't exactly done anything with the Godot yet. I've just been reading the documentation. It's a lot.
Damn.
Yeah, it's a
Just
lot.
read faster.
Do you realize there's like a lot?
No, there's not.
Yeah, there is. There's a lot of documentation. It's almost like it's trying to detail every bit of the game engine.
No, it's not.
What do you mean, no, it's not?
It means no, it's not.
God damn it, you're right.
I am right.
Yeah. Mr. Phoenix.
Phoenix right.
From the Ace Attorney series.
Okay. Actually,
To learn more on workspaces, read the 5 main scenes. To learn more on the 3D viewport and 3D in general, read Introduction to 3D. You know, I just figured that there's a possibility that you might want to see what I'm looking at.
nah. I'm doing other shit.
I said a possibility. On either side of the viewport, sit the dom.
Hey!
Ah! What?
I heard the conversation, so I had to scare you.
Naya tried. She failed.
But I didn't.
Because I figured she'd be coming this way. I didn't expect you
All of a
to.
sudden.
Yeah. Is that all? Okay. Okay. Get scared twice.
Good job.
Anyway.
I'm aware one of those was my fault, and it was
Yes.
funny. I'd do it again.
You would? Who would have guessed that? Shelby! Shelby! Joey, where's the pretty girl? Shelby. Shelby. Hey, dog. Shelby. Over here. Shelby. The dog doesn't want to say hi.
That's alright because I'm saying bye.
What? What? What?
Huh?
The scene dock lists the active scenes nodes. The inspector allows you to edit the properties of the selected node. Yep. Over here. That. No, that's the wrong one. Stardew Valley. To read more on Inspector, see Inspector Dock. Docks can be customized. Read more on the moving and resizing dock. The bottom panel, situated below the viewport, is the host of the debug console, the animator editor, the audio mixer, and more. They can take precious space, that's why they're folded by default. When you click one, it expands vertically. Below, you can see the animation editor opened. Ooh, fun. Bottom panels can also be shown or hidden using the shortcuts defined in the editor settings. Shortcuts under the bottom panels category. The 5 main screens. There is a 5 main screens button centered at the top of the editor. 2D, 3D, script, game, and asset library. You'll use the 2D screen for all types of games. In addition to 2D games, the 2D screen is where you'll build your interfaces. In the 3D screen, you can work with meshes, lights, and design levels for 3D games. Ooh. That looks cool. Wonder what game that's from. Maybe an extraction shooter. I don't know. Read the introduction to 3D for more detail about the 3D main screen. The game screen is where your project will appear when running it from the editor. You can go through your project to test it, and pause it and adjust it in real time. Note that this is for testing how adjustments would work. Any changes made here are not saved when the game stops running. Yep, just like most games. The script screen is a complete code editor with a debugger, rich auto-completion, and built-in code reference. Cool. Finally, the asset library is a library of free and open source add-ons, scripts, and assets to use in your projects. You can learn more about the asset library about the asset library. Is this also in the documentation? Yeah, it's in the documentation. And this is in the documentation? It's in the manual part of the documentation. Okay. However, these two things are not. Integrated class reference. Godot comes with a built-in class reference. You can search for information about a class, method, property, constant, or signal by any one of the following methods. Pressing F1 or Opt space on macOS or F1 for laptops with the FN key anywhere in the editor. Clicking the search help button in the top right of the script main screen. Clicking on the help menu and search help. Control click. Command click on macOS on a class name, function name, or built-in variable in the script editor. That's a few ways. Good to have a few ways. When you do any of these, a window pops up. Type to search for any item. You can also use it to browse available objects and methods. Damn. Double-click on the item to open the corresponding page in the script main screen. That made it sprite 2D. Alternatively, clicking while pressing Control on a class name, function name, or built-in variable in the script editor. Right-click on nodes and choosing Open Documentation, or choosing Lookup symbol for elements in the script editor will directly open their documentation. Cool. Wait, if that's the case, if that's the case, then wait. Huh, if that's the case, that I can just do that. And I think I can just fuck around with things. Confirmation dialog. We're gonna go through everything. See what everything does. That way we can properly look at the documentation. We'll go through this viewport one first. Guess not. Okay. Pop-up menu. Pop-up panel. Sub-viewport. And then sub-viewport. On that. Cool. We'll just continue doing it like this. Canvas item. Don't worry, Godot. I'm not doing anything weird. Just listing it in a way that looks and acts good. Or not acts good. This is purely just for documentation purposes. So that I can better read the documentation myself. Do 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 do. Do 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 do. Good God, there's a lot of shit. Bone 2D. There's just a lot of shit in one thing. I already had that one. I don't need a second. Canvas group. Canvas modulate. Collision polygon 2D. This will take a second. Jesus. Joint 2D. Okay. Ba-da-ba-da-ba-ba-ba. Yay. Rotate. Get comfy. I have no idea how long it's going to take to fuck around with all of this and learn it all. But we shall see. Line 2D. Marker 2D. Because let me expand everything. No, oh, we don't need to worry about that one. Control though. Brader, range, slider, scroll bar, text edit, base button, button, container. Oh geez. Container is big. Flow container, box container, V-box container, color picker. And the final one. Yeah, all of that. You go through all of that shit. Anyway, what was the last thing that we did? Marker 2D. Let us mesh instance. Multi-mesh instance. Navigation link. Navigation obstacle. Navigation region. I want to do it in order, bitch. Parallax 2D. Parallax layer. Path 2D. Path followed 2D. Polygon 2D. Raycast 2D. Remote transform 2D. Shapecast 2D. Skeleton 2D. I don't think I'll need that one based off of what it's called, but I'll read it anyway just in case. Sprite 2D. Tile map. Should that not be tile map 2D? Tile map layer. Touch screen button. I don't think I'm gonna need that one either. Visible on-screen notifier 2D. Maybe. Visible on-screen enabler 2D. Okay. I should probably still read the documentation even though I have all that available to me. Holy shit. Still a lot. Learning new features. Godot is a feature-rich game engine. There's a lot to learn about it. This page explains how you can use the online manual, built-in code reference, and join online communities to learn new features and techniques, making the most of this manual. What you are reading now is the user manual. It documents each of the engine's concepts and available features. When learning a new topic, you can start by browsing the corresponding section of the website. The left menu allows you to explore broad topics, while the search bar will help you find more specific pages. If a page exists for a given theme, it will often link to a more related content. Search docs. Oh, that's just an image. The manual has a companion class reference that explains each Godot class's available functions and properties when programming. While the manual covers general features, concepts, and how to use the editor, the reference is all about using Godot's scripting API application programming interface. You can access it both online and offline. We recommend browsing the reference offline from within the Godot editor. To do so, go to Help, search Help, or press F1. Press F1 for help. To browse it online, head to the manual's class reference section. A class reference page tells you where the class exists in the inheritance hierarchy. You can click the top links to jump to parent classes and see the properties and methods a type inherits. Ooh. stop exhaling gases in a non-breathing manner. It's annoying. A summary of the class's roles and use cases, an explanation of the class's properties, methods, signals, enums, and constants. Links to manual pages further detailing the class. If the manual or class reference is missing or has insufficient information, please open an issue in the official Godot docs GitHub repository to report it. You can hold Control and the mouse over text, like the name of the class, property, method, signal, or constant to underline it. Then Control click to jump to it. Learning to think like a programmer. I already know how to do that. Learning with the community. Godot has a growing community of users. Community tutorials. Character, wizard, warrior. Design philosophy. Now you've gotten your feet wet, let's talk about Godot's design. Every game engine is different and fits different needs. Not only do they offer a range of features, but the design of each engine is unique. This leads to different workflows and different ways to form your game's structures. This all stems from their respective design philosophies. This page is here to help you understand how Godot works, starting with some of the core pillars. It is not a list of available features, nor is it an engine comparison. To know if any engine can be a good fit for your project, you need to try it out for yourself and understand its design and limitations. Please watch Godot explained in 7 minutes if you're looking for an overview of the engine's features. Nah, I'm good. Object-oriented design and composition. Godot embraces object-oriented design as its core with its flexible scene system and node hierarchy. It tries to stay away from strict programming patterns to offer an intuitive way to structure your game. For one, Godot lets you compose or aggregate scenes. It's like nested prefabs. You can create a blinking light scene and a broken lantern scene that uses the blinking light. Then create a city filled with broken lanterns, change the blinking light's color, save, and all the broken lanterns in the city will update instantly. On top of that, you can inherit from any scene. A Godot scene could be a weapon, a character, an item, a door, a level, part of a level, anything you'd like. It works like a class in pure code, except you're free to design it by using the editor, using only the code or mixing and matching the two. It's different from the prefabs you find in several 3D engines, as you can then inherit from the and extend those scenes. You may create a magician that extends your character, modify the character in the editor, and the magician will update as well. It helps you build your projects so that their structure matches the game's design. Alright. Also note that Godot offers many different types of objects called nodes, each with a specific purpose. Nodes are part of a tree, always inherit from their parents up to the node class. Although the engine does feature some nodes like collision shapes that a parent physics body will use, most nodes work independently from one another. In other words, Godot's nodes do not work like components in some other game engines. Sprite 2D is a node 2D, a canvas item, and a node. It has all the properties and features of its 3 parents. Parent classes like transforms or the ability to draw custom shapes and render with a custom shader. All-inclusive package. Godot tries to provide its own tool to answer most common needs. It has a dedicated scripting, workspace, an animation editor, a tile map editor, a shader editor, a debug profiler, the ability to hot reload locally and on remote devices, etc. The goal is to offer a full package to create games and continuous user experience. You can still work with external programs as long as there's an import plugin available for Godot for it. That is also partly why Godot offers its own programming language, GDScript, along with C#. GDScript is designed for the needs of game developers and game designers, and is tightly integrated in the engine and the editor. GDScript lets you write code using an indentation syntax, and it dedicates types and offers a static languages quality quality of auto-completion. It is also optimized for gameplay code with built-in types like vectors and colors. Note that GD extension you can write high-performance code using compiled languages like C, C++, Rust, D, Hax, or Swift without recompiling the engine. Note that the 3D workspace doesn't feature as many tools as the 2D workspace. You'll need external programs or add-ons to edit terrains, animate complex characters, and so on. Godot provides a complete API to extend the editor's functionality using game code. See the Godot editor's Godot game below. Open source. Godot offers a fully open source codebase under the MIT license. This means that the codebase is free for anyone to download, use, modify, or share as long as its license file is kept intact. All technologies that ship with Godot, including third-party libraries, must be legally compatible with this open source license. Therefore, most parts of Godot are developed from the ground up by community contributors. Anyone can plug in proprietary tools for the needs of their projects. They won't ship with the engine. They just won't ship with the engine. This may include Google, AdMob, or Fmod. Any of these can come as third-party plugins instead. On the other hand, an open codebase means you can learn from and extend the game engine to your heart's content. You can also debug games easily, as Godot will print errors with a stack trace, even if they come from the engine itself. Note, this does not affect the work you do with Godot in any way. There is no strings attached to the engine or anything you make with it. Community driven, yeah, we've heard this a bunch of times already. The Godot editor is a Godot game. The Godot editor runs on the game engine. It uses the engine's own UI system. It can hot reload code and scenes when you test your projects, or run game code in the editor. This means you can use the same code and scenes for your games, or build plugins and extend the editor. This leads to a reliable and flexible UI system as it powers the editor itself. With the tool annotation, you can run any game code in the editor. RPG in a Box is a voxel RPG made with Godot. It uses Godot's UI tools for its node-based programming system. Put the tool annotation at the top of the GD script file and it will run in the editor. This lets you import and export plugins, create plugins like custom level editors, or create scripts with the same nodes and API you use in your projects. Note, the editor is fully written in C++ and is statically compiled into the binary. This means you can't import it as a typical project that would have a project.godot file. Separate 2D and 3D engines. Godot offers dedicated 2D and 3D rendering engines. As a result, the base unit for 2D scenes is pixels. Even though the engines are separate, you can render 2D and 3D, 3D and 2D, overlay 2D sprites and interfaces over your 3D world. Step by step. I'll be right back. had to say hi to a dog. You just have to. Alright. Step by step, the series builds upon the introduction to Godot, and will get you started with the editor and the engine. You'll learn more about nodes and scenes, code your first classes, and with GDScript, use signals to make nodes communicate with one another, and more. The following lessons are here to prepare you for your first 2D game. Step-by-step tutorial where you will code a game from scratch. By the end of it, you'll have the necessary foundations to explore more features in other sections. We also include links to pages that cover a given topic in depth where appropriate. Okay. Let's see. Interesting that it took us here next. Nodes and scenes. In overview of Godot's key concepts, we saw that a Godot game is a tree of scenes, and that each scene is a tree of nodes. In this lesson, we explain a bit more about them. You'll also create your first scene. Nodes. Nodes are the fundamental building blocks of your game. They are like the ingredients in a recipe. There are dozens of kinds that can display an image, play a sound, represent a camera, and much more. All nodes have the following characteristics: a name, editable properties. They receive callbacks to update every frame. You can extend them with new properties and functions. You can add them to another node as a child. The last characteristic is important. Together, nodes form a tree, which is a powerful feature to organize projects. Since different nodes have different functions, combining them produces more complex behavior. As we saw before, you can build a playable character that the camera follows using a character body 2D node, a sprite 2D node, a camera 2D node, and a collision shape 2D node. Scenes. When you organize nodes in a tree like our character, we call this construct a scene. Once saved, scenes work like a node types in the editor, where you can add them as a child of an existing node. In that case, the instance of the scene appears as a single node with its internals hidden. Scenes allow you to structure your game's code however you want. You can compose nodes to create custom and complex node types, like a game character that runs and jumps, a life bar, a chest with which you can interact, and more. The Godot editor essentially is a scene editor. It has plenty of tools for editing 2D and 3D scenes, as well as user interfaces. A Godot project can contain as many of these scenes as you want. The engine only requires one of your application's main scenes. This is the scene Godot will first load when you or a player runs the game. On top of acting like nodes, scenes have a following characteristic. They always have one root node, like the player in our example. You can save them in your local drive and load them later. You can create as many instances of a scene as you'd like. You could have 5 or 10 characters in your game created from your character scene. Creating your first scene. Let's create our first scene with a single node. To do so, you will need to create a new project. First, after opening the project, you should see an empty editor. In an empty scene, the scene dock on the left shows several options to add a root node quickly. 2D scene adds a node 2D node. 3D scene adds a node 3D node. And user interface adds a control node. These presets are here for convenience. They are not mandatory. Other node lets you select any node to be the root node. In an empty scene, other node is equivalent to pressing the add child node button at the top left of the scene dock, which usually adds a new node as a child of the currently selected node. We're going to add a single label node to our scene. Its function is to draw text on the screen. Press the add child node button or other node to create the root node. Other node. To create a new node, dialog opens showing the long list of available nodes. Select the label node. You can type its name to filter down the list. label. Click the label node to select it and click the create button at the bottom of the window. Where? Oh, I already did that. A lot happens when you add a scene's first node. The scene changes to the 2D workspace because label is a 2D node type. The label appears selected in the top left corner of the viewport. The node appears in the scene dock on the left, and the node's properties appear in the inspector dock on the right. Changing a node's properties. The next step is to change the label's text properties. Let's change it to Hello World. Head to the inspector dock on the right of the viewport, click inside the field below the text property, and type Hello World. Nope, wrong one. Nope, wrong one as well. Yay. Hello World. Like that? I think so. You will see the text drawn in the viewport as you type. Alright. See, also, you can edit any property listed in the inspector as we did in the text. For a complete reference of the inspector dock, see inspector dock. You can move your label node in the viewport by selecting the move tool in the toolbar. Move tool. Ah, cool. With the label selected, click and drag anywhere in the viewport to move it to the center of the view, delimited by the rectangle. No, I wanted that open. How big is the rectangle? Um, that looks like it's centered. Running the scene. Everything's ready to run the scene. Press the Run Current Scene button in the top right of the screen, or press F6. F. Okay, run. Oh, this should just... maybe. Yeah, okay. A pop-up invites you to save the scene, which is required to run it. Click the Save button in the file browser to save it as label.tcsn. To save the scene as dialogue, like other file dialogues in the editor, only allows you to save files inside the project. The res path at the top of the window presents the project's root directory and stands for the resource path. For more information about the file paths in Godot, see File System. The application should open in a new window and display the text Hello World. Close the window or press F8 to quit the running scene. Setting the main scene. To run our test scene, we use the Run Current Scene button. Another button to the next of it, Run Project, allows you to set the run of the project's main scene. You can also press F5 to do so. F5. F6. That seemed like it did the same thing. But that's because we only have so little in there. We don't exactly have much. Running the project's main scene is distinct from running the current scene. If you encounter unexpected behavior, check to ensure you're running the correct scene. A pop-up window appears and invites you to select the main scene. Scene has been defined. Select one. I already did that. Check the Select button in the file dialog that appears. Double-click the label TSCN. The demo should run again, moving forward every time you run the project. Godot will use this scene as a starting point. The editor saves the main scene's path in the Project Godot file in your project's directory, while you can edit this text directly to change projects in the settings. You can also use the project settings window to do so. For more information, see project settings. In the next part, we'll discuss another key concept in games and in Godot, creating instances of a scene. Who the hell messaged me? And why? Ah, my D&D group. Just to pull results. Alright. Cool. Oh, ended. May 16th. Okay. In 10 days. Alright. Creating instances. Note, this tutorial refers to instancing scenes in the editor. To learn how to instance scenes from code, see nodes and scenes instances. Godot's approach to instancing described below should not be confused with hardware instancing that can be used to render large amounts of similar objects quickly. See optimization using multi-meshes instead. In the previous part, we saw that a scene is a collection of nodes organized in a tree structure with a single node as its root. You can split your project into any number of scenes. This feature helps you break down and organize your game's different components. You can create as many scenes as you'd like and save them as files with the .tscn extension, which stands for text scene. The label tscn file from the previous lesson was an example. We call those files packed scenes, as they pack information about your scene's content. Here's an example of the ball. It's composed of a rigid body 2D node as its root named ball, which allows the ball to fall and bounce on walls, a sprite 2D node, and a collision shape 2D. As you have saved a scene, it works as a blueprint. You can reproduce it in other scenes as many times as you'd like. Replicating an object from a template like this is called instancing. Ah, very, very fun. Very, very good. Thinking about switching the camera from over here to be over here, because I keep looking over here when I'm talking to you guys. Would it look better that way? That's the question. Nope. It's farther away from my face. Then oh, by the way, if you want to see what I look at, okay. So when I try to look at you guys, I say, um, I don't look at the camera. I instead look at this little guy. I got this idea from a YouTuber named C.com. Should check him out. Very entertaining. Um, yeah, and I think it helps. I think it helps. Let's transform this. Flip horizontal. Okay. Yeah, that looks good. Once you have saved a scene, instancing. As we mentioned in the previous part, instancing scenes behave like a node. The editor hides their content by default. When you instance the ball, you only see the ball node. Notice how each duplicate has a unique name. Every instance of the ball scene starts with the same structure and properties as the ball TSCN. However, you can modify each independently, such as changing how they bounce, how heavy they are, or any property exposed by the source scene. Let's use instancing in practice to see how it works in Godot. We invite you to download the ball's sample project we prepared for you. Instancing starter.zip. Extract the archive on your computer to import it. You need the project manager, the project The project manager is accessed by opening Godot. Or if you already have Godot open, click on Project, quit to Project List. Yes. In the project manager, click the import button to import the project. What? Instancing starter.zip. Okay, I'm moving this over to this side so that I can read better. And you guys can look at what I'm doing more. Alright, downloads. Extract. Instancing starter. Download the ball's sample project we prepared for you. Extract the archive on your computer. To import it, you need the project manager. The project manager is accessed by opening Godot. Click project, quit to project list. Oh, I should documentation project. And then quit to project list. Ah, right there at the bottom. And then we import. Downloads. It's called instancing starter. Import and edit. In the project manager, click the import button to import the project. In the pop-up that appears, navigate to the folder you extracted. Double-click the project Godot file to open it. Finally, click the import button. The window notifying you that the project was last opened in an older Godot version may appear. That's not an issue. Click OK to open the project. The project contains two package scenes, main TSCN, containing walls against which the ball collides, and ball TSCN. Ah, here we go. And where's ball TSCN? Main scene should open automatically. If you're seeing an empty 3D scene instead of the main scene, click the 2D button at the top of the screen. Already figured that out. Let's add the balls as a child of the main node. In the scene dock, select the main node, then click the link at the top of the scene dock. This button allows you to add an instance of a scene as a child of the currently selected node. Let's just minimize all of these. Let's see. Scene, this one, ball, open. Aha! Probably have it in main, not, okay, and if we run this, will it does fall. Cool. Alright, let's stop it. Double click the ball scene to instance it. The ball appears in the top left corner of the viewport. Yes, it did. Click on it and drag towards the center of view. There. Play the game by pressing F5. You should see it fall. Now we can create more instances of the ball node, which we can select with the doll selected. ball selected, press Ctrl D to call a duplicate command. Click to drag and move the ball to a different location. Let's get a bunch in here. You can repeat this process until you have several in the scene. Play the game again, you should now see every ball fall independently from one another. This is what instances do. Each is an independent reproduction of a template scene, editing scenes and instances. There is more to instances. With this feature, you can change the properties of one ball without affecting the others using the inspector. Change the default properties of every ball by opening the ball TSCN scene, making a change to the ball node there. Upon saving, all instances of the ball in the project will see their values update. Change a property on the instance always overrides values from the corresponding pack scene. Let's try this, double click. Okay, I just want to run this real quick, see how the physics engine handles it. Okay, that wasn't as exciting as I would have hoped. Okay. Change the properties of one ball without affecting the others using the inspector. Change the default properties of every ball by opening the ball TSCN scene and making a change to the ball node there. Upon saving, all instances of the ball project will see their values update. Change a property on the instance always overrides a value from the corresponding pack scene. Let's try this. Double click the ball TSCN in the file system to open it. In the scene dock on the left, select the ball node. Oh, right here. Then, in the inspector on the right, click on the physics material property to expand it. Physics. Has physics. Expand. Okay. So it doesn't expand for me, but I can still... What? Oh, okay. There we go. Set its bounce property to 0.5. Bounce 0.5. Clicking on the number field, typing 0.5 and pressing enter. Play the game by pressing F5 and notice how balls now bounce a lot more. Nope. F5 in here. Now that's more entertaining. Should probably up the friction on that. Now just individual instance, head back to the main scene and clicking the corresponding tab above the viewport. Main. Main. Oh, okay. Now I can just switch between the two. Select one of the instance ball nodes and the inspector set its gravity scale to 10. Let's say this one. 10. A gray reverb button appears next to the adjusted property. This icon indicates you're overriding a value from the source packaged scene. Even if you modify the property in the original scene, the value override will be preserved in the instance. Clicking the revert icon will restore the property to the value of the saved scene. Rerun the game and notice how this ball falls much faster than the others. It does, you're right. Makes things a lot more interesting. Note, you may notice you are unable to change the values of physics materials of the ball. This is because physics materials is a resource and needs to be made unique before you can edit it in a scene. That is linking to the original scene. To make resource unique for one instance, right-click on the physics material property in the inspector and click Make Unique. Shelby. Hey. Shelby. Hello. You wanna hang out in here with me? How's that sound? How's that sound? Here, let me set up a blanket for you so you can be comfy on the floor and with me. Oh, I'm trying. I'm trying. Come on, lay down. Lay down. Come on. There you go. Okay. No, what you doing? You just licking the floor? Of course you are. Scene instances as a design language. Instances and scenes in Godot offer an excellent design language setting at the engine apart from others out there. We designed Godot around this concept from the ground up. We recommend dismissing architectural code patterns when making games with Godot, such as model view controller, MVC, or entity relationship diagrams. Instead, you can start by imagining the elements players will see in your game and structure your code around them. For example, you could break down a shooter game like so. I could read and understand that, but I won't. You can come up with a diagram like this for almost any type of game. Each rectangle represents an entity that's visible in the game from the player's perspective. The arrows point towards the instantiator of each scene. Once you have a diagram, we recommend creating a scene for each element listed in it to develop your game. You'll use instancing either by code or directly in the editor to build your tree of scenes. Programmers tend to spend a lot of time designing abstract architectures and trying to fit components into it. Designing based on scenes makes development faster and more straightforward, allowing you to focus on the game logic itself. Because most game components map directly to a scene, using a design based on a scene instantiation means you need little over architectural code. Little other architectural code. Here's the example of a scene diagram for an open world game with tons of assets and nested elements. Yep. Imagine we started by creating the room. We could make a couple of different room scenes with unique arrangements of furniture in them. Later we could make a house scene that uses multiple room instances. For the interior, we could create a citadel out of many instanced houses and a large terrain on which we would place the citadel. Each of these would be a scene instancing one or more subscenes. Later, we would create scenes representing guards and add them to the citadel. They would be indirectly added to the overall game world. With Godot, it's easy to iterate on your game like this, as all you need to do is create the instantiate more scenes. We designed the editor to be accessible to programmers, designers, and artists alike. A typical game development process can involve 2D or 3D artists, level designers, game designers, and animators, all working with the Godot editor. Summary: instancing the process of producing an object from a blueprint has many handy uses. With scenes, it gives you the ability to divide your game into reusable components, a tool to structure and encapsulate complex systems, a language to think about your game project structure in a natural way. Scripting languages. This lesson will allow you to overview the available scripting languages in Godot. You will learn the pros and cons of each option. In the next part, you will write your first script using GDScript. Scripts attach a node and extend its behavior. This means that scripts inherit all functions and properties of the node they attach to. For example, take a game where a camera 2D node follows a ship. The camera 2D node allows its parent by default. Imagine you want the camera to shake when the player takes damage. As this feature is not built in Godot, you would attach a script to the camera 2D node and code to shake. Available scripting languages. Godot offers 4 gameplay programming languages: GDScript, C#, and via its GD extension technology, C and C++. There are more community support languages that you can mold with that. Which language should I use? GDScript is an object-oriented and imperative programming language for built-in. It's made by simple syntax. Blah blah blah. I think I can just skip over this part. Creating your first script. In this lesson, you will code your first script to make the Godot icon turn in circles. As we mentioned in the introduction, we assume you have programming foundations. This tutorial is written for GDScript, and the equivalent C# code is included in another tab of each code block for convenience. To learn about GDScript, its keywords, and its syntax, head to the GDScript section. To learn more about C#, head to C#/.net section. Project setup. Please create a new template to start with a clean slate. Scene. New scene. Oh, new project. No, project. Quit to project list. Create. Yeah, just create new game project. Need to create a sprite 2D node to display it in the game. In the scene dock, click the other node button. Sprite 2D. Where is it? Here? Yeah, there. To create the node, your scene should be empty and only have a 2D sprite. Sprite 2D node needs a texture to display. In the inspector on the right, you can see the texture properties say empty. To display Godot engine, click and drag the icon SVG from this file system in the dock texture slot. Boop. Cool. You can create Sprite 2D nodes automatically by dragging and dropping images in the on the viewport. Then click and drag the icon in the viewport to center it in the game view. Um, 1150, 650. So 325 and 575. Yeah. To create and attach a new script to our node, right-click on the Sprite 2D on the scene dock and select Attach Script. The Attach Node script windows appear. It allows you to select the script's language and file path, among other options. Change the template from node default to object empty. To start with a clean file, leave the other options set to their default values and click the empty button to create the script. Did I say empty? I meant create button. Create. Yay! C# names need to match their class name. In this case, you should name the file mysprite2d. It's fine. The script workspace should appear with your new sprite2d GD file open and following the line of code. Extends sprite2d. Every GD script file is implicitly a class. The extends keyword defines the class this script inherits or extends. In this case, it's sprite2d, meaning our sprite will get access to all the properties and functions of the sprite2d node, including classes classes that extends, like Node2D, Canvas item, and Node. In GDScript, if you omit the line with the extends keyword, your class will implicitly extend ref counted, which Godot uses to manage your application's memory. Inherited properties include the one you see in the inspector doc, like our node's texture. By default, the inspector displays a node's properties in title case with capitalized words separated by a space. In GDScript code, these properties are in snake case, which is lowercase with each word separated as an underscore. You can hover over any property's name in the inspector to see a description and its identifier in code. Hello world, our script currently doesn't do anything. Let's make it print the text hello world to the output bottom panel to get started. Add the following code to your script. Alright. Function underscore init. Print. That's not how you spell hello. Hello world. Yay. Let's break it down. The function keyword defines a new function named underscore init. This is a special name for our class's constructor. The init calls underscore init on every object or node upon creating it in memory if you define this function. Note, GDScript is an indent-based language. The tab at the start of the line says the print is necessary for the code to work. If you omit it or don't indent a line correctly, the editor will highlight it in red and display the following error message: indented block expected. Save the scene as Sprite2D TSCN if you haven't already. Then press F6. I can just press F6 and it do that. Boom. And hello world. To run it, look at the output bottom panel that expands. It should say hello world. Delete the init function so you're only left with the extend Sprite2D. Turning around, it's time to make our node move around. To do so, we're going to add two member variables to the script: the movement speed in pixels per second and the angular speed in radians per second, and the following after the extends sprite line. Alright. Variable speed equals 400. Variable angular speed equals pi. Oh, pi. Member variables sit near the top of the script after any extends lines, but before functions. Every node instance with this script attached to it will have its own copy of the speed and angular speed properties. Note, angles in Godot work in radians by default, but you have built-in functions and properties available if you prefer to calculate angles in degrees instead. To move our icon, we need to update its position and rotation every frame in the game loop. We can use the underscore process virtual function of the node class. If you define it in any class that extends the node class, like Sprite2D, Godot will call the function every frame and pass it an argument named delta, the time elapsed since the last frame. Games work by rendering many images per second, each called a frame, and they do so in a loop. We measure the rate at which a game produces images in frames per second, FPS. Most games aim for 60 FPS, although you might find figures like 30 FPS on slower mobile devices or 90 to 240 for virtual reality games. The engine and game developers do their best to update the game world and render images at the constant time interval, but there are always small variations in frame render times. That's why the engine provides us with the delta time value. Make our motion independent of our frame rate. At the bottom of the script, define the function. Alright. Function underscore process delta rotation plus equals angular speed times delta. The func keyword the function keyword defines a new function. After it, we have to write the function's name and arguments it takes in parentheses. A colon ends the definition, and the indented blocks that follow are the function's content or instructions. Notice how underscore process, like underscore init, starts with the leading underscore by convention. Godot's virtual functions, that is to say built-in functions you can override to communicate with the engine, start with an underscore. The line inside the function, rotation plus equals angular speed times delta, increments our sprite's rotation every frame. Here, rotation is a property inherited by the class node2d, which sprite2d extends it, controls the rotation of our node, and works with radians. In the code editor, you can control-click on any built-in property or function like position, rotation, or underscore process to open the corresponding documentation in a new tab. Run the scene to see the Godot icon turn in place. Select current. Yay! Note, in C#, notice how the delta argument taken by underscore process is a double. We therefore need to convert it to a float when we apply it to the rotation. Moving forward, let's now make the node move. Add the following two lines inside the underscore process function, ensuring the new lines are indented the same way the rotation plus equals angular speed times delta line before them. Alright. So I assume then variable velocity equals vector 2 dot up dot rotated rotation times speed position plus equals velocity times delta. There we go. As we already saw, let me play that. As we already saw, whoa, okay. Why did it crash? Or did it not? Did it not crash? What? What did I do wrong? Here, I'm just gonna... Boop. Okay. Let's try it this time. What? What? What did I do wrong? What? What? Variable speed. Angular speed. What? Alright, I'm just going to copy and paste this here. That was the same thing. Process delta and do that. I'm gonna grab this and do that. Why does it go forward? So we already saw the variable keyword defines a new variable. If you put it at the top of the script, it defines a property in the class inside a function. It defines a local variable. It only exists within the function scope. We define a local variable named velocity, a 2D vector representing both a direction and a speed. To make the node move forward, we start with the vector 2's class constant vector 2 up, a vector pointing up, and rotate it by calling the vector 2 method rotated. This expression, vector 2 up rotated rotation, is a vector pointing forward relative to our icon, multiplied by our speed property. It gives us a velocity we can use to move the node forward. We add velocity times delta to the node's position to move it. The position itself is a type of vector. It is of type vector 2, a built-in type in Godot's Godot representing a 2D vector. Run the scene and see Godot head run in circles. What if I change that to delta? Would it then? No, what? Complete script. What? Oh, you've got to be kidding me. Missed the... Oh, wait. Okay. Alright. Okay. Listening to player input. Building upon the previous lesson, creating your first script, let's look at another important feature of any game, giving the control to the player. To add this, we need to modify our sprite2d.gd code. You have two main tools to process the player's input in Godot. The built-in input callbacks, mainly unhandled underscore input like process. It's a built-in virtual function that Godot calls every time the player presses a key. It's the tool you want to use to react to events that don't happen every frame, like pressing space to jump. To learn more about input callbacks, see using input event. The input singleton, a singleton is a globally accessible object. The Godot provides access to several in scripts. It's the right tool to check for input every frame. We're going to use the input singleton here as we need to know if the player wants to return or move every frame. For returning, we should use a new variable, direction, in our process function. Replace the rotation plus equals angular speed times delta line with the code below. Variable direction equals 0. If input dot is action underscore pressed UI underscore left. Direction equals -1. If input dot is action underscore pressed UI underscore right. Need to change that. Direction equals 1. Rotation plus equals angular plus equals angular speed times direction times delta. What did I do wrong? Verbal direction equals 0. Input is action pressed, UI left. Direction equals -1 if input is action pressed, UI right. Direction equals 1. And then rotation plus equals angular speed times direction times delta. What did I do wrong? Then, okay. Alright. To produce these values, we introduce conditional statements and the use of input as a conditional statement if statement starts with the if keyword in GD script and ends with a colon. The condition is specifically the expression between the keyword and the colon at the end of the line. To check if a key was pressed this frame, we call input is action pressed. The method takes a text string representing an input action and returns true if the action is pressed, false otherwise. The two actions we use above, UI left and UI right, are defined in every Godot project. They respectively trigger when the player presses the left and right arrows on the keyboard or left and right on a game's D-pad. Note, you can use and edit input actions if your project is going to project settings, clicking on the input map tab. Finally, we use the direction as a multiplier when we update the node's rotation. Rotation plus equals angular speed times direction times delta. Comment out the lines, variable velocity equals vector up rotated rotation times speed, and position plus equals velocity times delta, like this. This will ignore the code that moved the icon's position in the circle without user input from the previous exercise. If you run the scene with the code, the icon should rotate when you press left and right. Yep. Moving when pressing up. To only move when pressing a key, we need to modify the code that calculates the velocity. Uncomment the code and replace the line starting with var velocity with the code below. I'm not going to uncomment it. Instead, I'm just going to do this. Variable velocity, because it's better to, it helps to remember this way. Vector 2.0. If input dot is action or pressed UI underscore up velocity equals vector 2 dot up dot rotated rotation times speed is action pressed. This feels kind of reminiscent of this movement feels very reminiscent of asteroids. We initialize the velocity of vector we initialize the velocity with a value of vector to 0, another constant of the built-in vector type, representing a 2D vector of length 0. If the player presses the UI up action, we then update the velocity's value, causing the sprite to move forward. Complete the script. Here is a complete sprite 2D GD file for reference. If you run the scene, you should now be able to rotate with the left and right arrow keys and move forward by pressing up. Summary. Blah, blah, blah. I already got it. Using signals. In this lesson, we will look at signals. They are messages that nodes emit when something specific happens to them. Like a button being pressed, other nodes can connect to that signal and call a function when the event occurs. Signals are a delegation mechanism built into Godot that allows one game object to react to a change in another without them referencing one another. Using signals limits coupling and keeps your code flexible. For example, you might have a life bar on the screen that represents the player's health. When the player takes damage or uses a healing potion, you want the bar to reflect the change. To do so, in Godot, you would use signals. Like methods callable, signals are a first-class type since Godot 4.0. This means you can pass them around as method arguments directly without having to pass them as strings, which allows for better auto-completion and is less error-prone. See the signal class reference for a list of what you can do with the signal types directly. See also, as mentioned in the introduction, signals are Godot's version of the observer pattern. You can learn more about it in the game programming patterns. We will now use a signal to make our Godot icon from the previous lesson, listening to player input, move, and stop by pressing a button. For the project, we will be allowing the Godot naming conventions. Duty script, classes, nodes, scenes, blah blah blah. Scene setup. To add a button to our game, we will create a new scene which will include a button and the Sprite 2D TSCN scene we created in the Creating Your First Script lesson. Create a new scene by going to Menu, Scene, New Scene. Scene, New Scene. In the scene, click the 2D Scene button. This will add a node 2D as our root. In the file system dock, click and drag the Sprite 2D TSCN file you saved previously into the node 2D to instantiate it. So just grab this and drag it here. Okay. In the file system, node to instantiate it. We will add another node as a sibling of the Sprite 2D. To do so, right-click on Node 2D and select Add Child Node. Search for the button node and add it. Button. Button. The node is small by default. Click and drag on the bottom right handle of the button in the viewport to resize it. 2D. Grab this. Rather large button, but oh well. If you don't see the handles, ensure the select tool is active in the toolbar. Click and drag on the button itself to move it closer to the sprite. Closer. You can also write a label on the button by editing its text property in the inspector. Enter toggle motion. What? Text. Toggle motion. Your scene tree and viewport should look like this. Okay, I'll just set it there. Save your newly created scene as node TD TSN. Control S. Alright. If you haven't already, you can run it with F6. At the moment, the button will be visible, but nothing will happen if you press it, connecting a signal in the editor. Inspector. Here we want to connect a button press signal to our Sprite 2D, and we want to call a new function that will toggle its motion on and off. We need to have a script attached to the Sprite 2D node, which we do from the previous lesson. You can connect signals in the signal dock, select the button node, and on the right side of the editor, click on the tab named Signals next to the inspector. What? Inspector. What? I do not see that. So we got that. Then it has inspector signals and groups. Node. Maybe it's just in node then. The dock displays a list of signals available on the selected node. Double-click the pressed signal to open the node connection window. Base button pressed. There you can connect the signal to the Sprite 2D node. The node, and then the node needs a receiver method, a function that Godot will call. The button emits the signal. The editor generates one for you. By convention, we name these callback methods on node name signal name. Here it'll be on button pressed. Yep, and just connect. Cool. Pass. When connecting signals via the editor's signal dock, we can use two modes. The simple one only allows you to connect to nodes that have a script attached to them and creates a new callback function on them. The advanced view lets you connect to any node and any built-in function and add arguments to the callback and set options. You can toggle the mode in the Windows bottom right by clicking the Advanced button. If you are using an external editor, such as VS Code, this automatic code generation might not work. In this case, you need to connect the signal via code as explained in the next section. Click the Connect button to complete the signal connection and jump to the script workspace. You should see the new method with a connection icon in the left margin. Yes, yes. If you click the icon, a window pops up and displays information about the connection. This feature is only available when connecting nodes in the editor. Like that? Yep. Let's replace the pass keyword with the code that'll toggle the node's motion. Our Sprite 2D moves thanks to code in the process function. Godot provides a method to toggle processing on and off, node set process. Another method of the node class is processing, returns true if idle processing is active, when we use the not keyword to invert the value. Alright. Function on set underscore process. Not is processing. That's what it wants me to set it as. This function will toggle processing and in turn the icon's motion on and off, pressing the button. Before trying the game, we need to simplify our underscore process function to move the node automatically and not wait for user input. Place it in the following code, which we saw 2 lessons ago. Function process delta variable rotation plus equals angular speed times delta. Variable velocity equals vector 2 dot up dot rotated rotation times speed. And then we want position plus equals velocity times delta. Your complete Sprite 2D GD code should look like the following. On the current scene by pressing F6 and click the button to see the sprite start and stop. Whoa. Debug. What the? Okay. Nope. Copy. Control A, paste. And now it should work. What? Debug. Oh. Considering all of this is just one thing. Rotation plus equals angular speed times delta. Variable velocity equals vector 2 dot up dot rotated rotation times speed position equals plus, no, plus equals velocity times delta. Alright, now it should function. Current by pressing F6. Click on the button to see the sprite start and stop. What? 2D. Script. Run. There should be a button. Play this scene. Okay. There we go. Connecting a signal via code. You connect signals via code instead of using the editor. This is necessary when you create nodes or instantiate scenes inside of a script. Let's use a different node here. Godot has a timer node that's useful to implement skill cooldown times, weapon reloading, and more. Head back to the 2D workspace. You can either click the 2D text at the top of the window or press Ctrl F1. In the scene dock, in the scene dock, right-click on the Sprite 2D node and add a new child node. Search for a timer and add the corresponding node. Your scene should look like this. Timer. Great. With the timer node selected, go to the inspector and enable the auto start property. Click on the script icon next to the Sprite 2D to jump back to the scripting workspace. We need to do 2 operations to connect the nodes via code. Get a reference to the timer from Sprite 2D, call the connect method on the timeout signal. To connect a signal note to connect to a signal via code, you need to call the connect method of the signal you want to listen to. In this case, we want to listen to the timer's timeout signal. We want to connect the signal when the scene is instantiated, and we can do that using the node ready built-in function, which is called automatically by the engine when a node is fully instantiated. To get a reference to a node related to the current one, we use the method nodeGetNode. We can store the reference in a variable. Gonna make this smaller. Alright. Function ready variable timer equals get node timer. The function getNode looks at the script2D's children and gets nodes by their name. For example, if you renamed the timer node to blinking timer in the editor, you would have to change the call to getNode blinking timer. We can now connect to the timer to use the Sprite2D in the ready function. Function ready, right? Timer.timeout.connect underscore on timer timeout. Okay, I'll just copy and paste the function if you want to be like that. What? Bear on not declared in current scope. What? The line reads like so. We connect to the timer's timeout signal to the node to which the script is attached. When the timer ends, or when the timer emits timeout, we want to call the function onTimerTimeout, what we need to define. Let's add it to the bottom of the script and use it to toggle our sprite's visibility. By convention, we name these callback methods to GDScript as on node name signal name, and in C# as on node name signal name. Here it'll be on timer timeout for GDScript and on timer timeout for C#. Okay. So it's fine. Okay, function on timer timeout. The visible property is a boolean that controls the visibility of our node. The line visible equals not visible toggles the value. If visible is true, it becomes false, and vice versa. If you run the node scene now, you'll see the sprite blinks on and off at 1 second intervals. That's it for a little. Here's the file for reference. Okay. Let's run it. Oh. What went wrong? 2D. Run. Invalid access to property or key timeout on a based object of type null instance. What? Ready node not found. Timer relative to root. Stack trace. Okay, we are just going to grab this, Control paste, and of course, what? Section is reference to define user-owned signals and does not build upon the project created in the previous lesson. You can define custom signals in a script. Say, for example, that you want to show a game over screen when the player's health reaches 0. To do so, you could define a signal named died or health depleted when their health reaches 0. Your signals work the same way as built-in ones. They appear in signals to the tab, and you can connect to them like any other. To emit a signal in your script, call emit signal. What? Invalid access to property or key timeout on a based object or type null instance. What? Godot error. Invalid access to property or key timeout on a base object of type null instance. Oh. What is this? Let's see. Still no chatters. Property based on could you please try and run your game while the game is running? Check the remote tab of scene. Can you try following instead? Response. I have it because the game says because it crashes on startup on the null error. However, I comment out the offending script and run the game. I do indeed have the game node there. Other nodes, including this one, as children of it. So it's this one? That's messing up? Yes. Okay, let's try F5. F6. F6. Cool. Alright. I was just pressing the wrong button, I think. Okay. Alright. You can define custom signals in a script, say for example, that you want to show a game over screen when the player's health reaches 0. To do so, you could define a signal named died, or health depleted when their health reaches 0. Let's just minimize all of these. Signal health deleted variable health equals 10. As signals represent events that just occurred, we generally use an action verb in the past tense in their names. Your signal works the same way as built-in ones. They appear in the Signals tab, and you can connect to them like any other. To emit a signal in your scripts, call emit on the signal. Function take damage. Amount health minus equals amount. If health is less than or equal to 0, health depleted dot emit. Health. Wait, no. Oh. A signal can optionally be declared can declare one or more arguments. Specify the argument names between parentheses. Signal health changed. Old value. New value. Note, the signal arguments show up in the editor's signal doc, and Godot can use them to generate callback functions for you. However, you can still emit any number of arguments when you emit signals, so it's up to you to emit the correct values. To emit values along the signal, add them as arguments to the emit function. Function take damage amount. Variable old health equals health. Health minus equals amount. Health underscore changed dot emit. Old health help. Alright. Summary. Yeah. Your first 2D game. In this step-by-step tutorial series, you'll create your first complete 2D game with Godot. By the end of the series, you'll have a simple yet complete game of your own, like the image below. You'll learn how the Godot, blah blah blah, prerequisites, contents. In the short part, we will set up and organize the project, launch Godot, and create a new project. Same code. And relaunch Godot. Only need one. Downloads. When creating the new project, you only need to choose a valid project path. You can leave the other default settings alone. Duty script. Download the Dodge the Creeps 2D asset zip. The archive contains the images and sounds you'll be using to make the game. Extract the archive and move the art and fonts directories to your project's directory. Test game in Forward Plus. Create and edit. Oh shit. I think it's a 2D scene. Create a new project, you only need to choose a valid project path. You can leave the other default settings alone. Your project folder should look like this. The game is designed for portrait mode, so we need to adjust the size of the game window. Click on project settings. To open the project settings window. In the left column, open the display window tab. There, set the viewport width to 480. 480. And viewport height to 720. You can see the project menu on the upper left corner. Also, under the stretch option, set mode to canvas items. And aspect to keep. This ensures that the game scales consistently on all different size screens. Organizing the project. In this project, we will make 3 independent scenes, player, mob, and HUD, which will combine into the game's main scene. In a larger project, it might be useful to create folders to hold various scenes and their scripts, but for this relatively small game, you can save your scenes and scripts in the project's root folder, identified by res. You can see your project's folders in the file system docs in the lower left corner. With the project in place, we are ready to design the player scene next lesson. Creating the player scene. With the project settings, and I should close this now. With the project settings in place, we can start working on the player-controlled character. The first scene will define the player object. One of the benefits of creating a separate player scene is that we can test it separately, even before we've created the other parts of the game. Node structure. To begin, we need to choose the root node for the player object as a general rule. As a general rule, a scene's root node should reflect the object's desired functionality. What the object is in the upper left corner in the scene tab is click the other node button and add an area 2D node to the scene. Godot also provides scene, new scene, other node. Godot also provides the character 2D node, specifically the designer 2D characters, which includes built-in support for some of the processes explained in this tutorial. In many real-world projects, character body 2D would be a better choice for players and enemies. However, this tutorial focuses on core concepts that apply to a wider range of nodes and use cases. Add area 2D. Great. When you add the area 2D node, Godot will display the following warning icon next to it in the scene tree. Yep. This warning tells us that the Area 2D node requires a shape to detect collisions or overlaps. We can ignore the warning temporarily because we will first set up the player's visuals using an animated sprite. Once the visuals are ready, we will add a collision shape as a child node. This will allow us to accurately size and position the shape based on the sprite's appearance. With Area 2D, we can detect objects that overlap or run into the player. Change the node's name to player by double-clicking on it. By double-clicking on it. Now that we've set the scene's root node, we can add additional nodes to give it more functionality. Before we add any children to the player node, we want to make sure we don't accidentally move or resize them by clicking on them. Select the node and click the icon in the right of the lock. Its tooltip says groups the selected node with its children. This causes the parent to be selected and any child node is clicked in 2D and 3D view. So this and then this button. Right? Okay, so it's there. Save the scene as player TSCN. Click scene save or press Control S. Control S. Player. For this project, we will be following the Godot naming conventions. GD script classes nodes use Pascal case, variables and functions use snake case, and constants use all caps. Okay. Sprite animation. Click on the player node and add Control A child node. Animated sprite 2D. Great. The animated sprite 2D will handle the appearance and animations for our player. Notice that there is a warning symbol next to the node. An animated sprite 2D requires a sprite frames resource, which is a list of animations it can display. Make sure animated sprite 2D is selected and then find sprite frames property under the animation section in the inspector and click empty. Okay. First, no, I didn't want to open that. Extract all. Extract. Here's the files. Instancing starter. Wait. Assets. Wanted me to add in what? Gonna have to go back. Previous. Archive and move the arts and fonts directories to your project folders. Oh. This we extract, not the other one. Boop. Okay, now we can move on to what we were doing. Sprite frames. Okay, click on the player node and add a child node. The animated sprite will handle appearance and manage to notice that they're warning that resources and animations. Make sure the animated sprite is selected, then find the sprite frames property under the animation. Animation, sprite frames. To the animation, select a section in the inspector and click empty. New sprite frames. Click on the sprite frames you just created to open the sprite frames panel. Alright. On the left is a list of animations. Click the default one and rename it to walk. Walk. Then click the add animation button to create a second animation named up. 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 Find the player images in the file system doc. They're in the art folder you unzipped. Drag the two images for each animation into the animation frames side of the panel for the corresponding animation. Art folder and drag the two images for each animation into the animation frame side. Corresponding animation. Player gray walk 1 and player gray walk 2. Boop. And up as well. Hello, who is it?
Hello, who is it? Balls.
Balls, welcome back.
Balls, welcome back.
What you doing?
Literally nothing. I'm just bored.
You're just bored, so you figured you might as well come and hang out with me while I'm learning Godot.
Yeah.
Yeah. Well, you have fun with that. I'm gonna continue my rampage. The player images are a bit too large for the game window, so we need to scale them down. Click on the Animated Sprite 2D node and set the scale property. Scale. Speed scale. Node 2D transform. Scale. To 0.5 and 0.5. You can find it in the inspector under the Node 2D heading. Finally, add a collision 2D shape, or collision shape 2D as a child of player. Collision shape 2D. This will determine the player's hitbox or the bounds of the collision area for this character. A capsule shape 2D node gives the best fit. So next to the shape on the inspector, click empty, then new capsule shape 2D. Capsule shape 2D. Using the two size handles, resize the shape to cover the sprite. We'll do that. Oh, interesting. Alright. Perfect. When you're finished, your player scene should look like this. Yep. Once this is done, the warning on the Area 2D node will disappear as it now has a shape assigned and can interact with the other objects. Make sure you save the scene again after these changes. Next part, coding the player. In this lesson, we will add the player movement animation and set it up to detect collisions. To do so, we need to add some functionality that we can't get from a built-in node. So we'll add a script. Click the player and add the node and click the attach script button. Player. In the script settings window, you can leave the default settings alone. Just click create. Note, if you are creating a C# script or other languages, select the language from the language drop-down menu before hitting create. If this is your first time encountering 2D script, please read scripting languages before continuing. Start by declaring member variables this object will need. Right. Nope. At export variable speed equals 400. Variable screen score size. Using the export keyword on the first variable, speed allows us to set its value in the inspector. This can be handy for values that you want to be able to adjust just like the node's built-in properties. Click on the player node and you'll see the property now appears in the inspector in the new section with the name of the script. Remember, if you change the value here, it will override the default value specified in the script. The script won't be modified. If you're using C#, you need to rebuild the project assemblies when... Oh, that's just for... Okay. Your player duty script should already contain a _ready and _process function. If you didn't select the default template shown above, create these functions while following the lesson. The ready function is called when a node enters the scene tree, which is a good time to find the size of the game window. In ready. Screen size equals get viewport _rect dot size. Now we can use the process function to define what the player will do. Process is called every frame, so we'll use it to update elements of our game, which we expect will change often. For the player, we need to do the following: check for input, move in the given direction, play the appropriate animation. First, we need to check for input. Is the player pressing a key for the game? We have 4 direction inputs to check. Input actions are defined in the project settings under Input Map. Here you can define custom events and assign different keys, mouse events, or other inputs to them. For this game, we will map the arrow keys to the 4 directions. Click on Project Settings to open the Project Settings window and click on the Input Map tab at the top. Type Move Right in the top bar and click the Add button to add Move Right direction. Project Settings, and Input Map. Move Right, Add. Okay. We need to assign a key to this section. Click the plus icon on the right to open the Event Manager window. The listening for input field should now automatically be selected. Press the right on your keyboard and the menu should look like this now. Listening for input, right. Click the OK button. The right key is now associated with the move right action. Repeat these steps to add 3 more mappings. Move left. Move up. And move down. Hello, Jesse.
Howdy.
How are you?
What?
How are you?
What?
How are you?
Good.
Good. You should be, you should go and search for jobs.
I'm eating.
Once you're done eating. I feel like that should be a given. Your input map tab should look like this. Yes. Click the close button to close the project settings. Note, we only mapped 1 key to each input action, but you can map multiple keys, joystick buttons, or mouse buttons to the same input action. You can detect whether a key is pressed using input is action pressed, which returns true if it's pressed, or false if it isn't. Alright. Process. Variable velocity equals vector 2 dot 0 if input dot is action underscore rest move right velocity dot x plus equals 1. If input dot is action underscore pressed move left velocity dot x minus equals 1. If input be easier if I just do this. Move right. Move. Who left?
Jesse did.
Okay. X. Y. Y. Down, up. And then if velocity dot length is greater than 0, velocity equals velocity dot normalized speed. $, animated sprite to D dot play. Else animated sprite 2D dot stop. What? I think somebody knocked on the door. I'll go check that out. I guess it was nothing. Alright. Ethan, are you still here? Or did you leave?
Yep.
Okay. And Jesse's still gone. Wonder where he went. Velocity not declared in the current scope. Oh, that's why. There we go. We start by setting the velocity to 0, 0 by default. The player should not be moving. Then we check each input and subtract the velocity to obtain a total direction. For example, if you hold right and down at the same time, the resulting velocity vector will be 1, 1. In this case, since we are adding a horizontal and vertical movement, the player would move faster diagonally than if it moved horizontally. We can prevent that if we normalize the velocity, which means we set its length to 1, then multiplied by the desired speed. This means no more fast diagonal movement. If you never used vector math before or need a refresher, you can see an explanation of vector. We can also check whether the player is moving, so we can call, play, or stop the animated sprite 2D. Tip, $sign is shortened for get node, so in the code above, $sign animated sprite 2D dot play is same as get node that. In GD script, $sign returns a node at the relative path from the current node. Returns null if the node is not found. Since animated sprite 2D is a child of the current node, we can use $sign animated sprite 2D. Now that we have a movement direction, we can update the player's position. We can also use a clamp to prevent it from leaving the screen. Clamping a value means restricting it to a given range. Add the following to the bottom of the process function. Make sure it is not indented under the else. Position plus equals velocity times delta. Position equals position dot clamp vector 2 dot 0 screen size. Tip, the delta parameter in the process function refers to the frame length, the amount of time that the previous frame took to complete. Using this frame ensures your movement will remain consistent even if the frame rate changes. Click Run Current Scene and confirm you can move the player around the screen in all directions. Oh, whoa. And now, there we go. If you get an error in the debugger panel that says attempt to call function plane based null instance. Okay. Choosing animations. Now the player can move. We need to walk. We need to change which animation the animated sprite 2D is playing based on its direction. We have the walk animation, which shows the player walking to the right. This animation should be flipped horizontally using the flip H property for left movement. We also have the up animation, which should be flipped vertically with flip V for downward movement. Let's place this code at the end of the process function. Sure. If velocity.x is not equal to 0, $, animated sprite 2D dot animation equals walk. $, animated sprite 2D dot flip underscore v equals false. $, animated sprite 2D dot flip underscore h equals velocity
Balls.
x balls. What? Why balls? Ethan, why balls? Oh well. Do animation equals up dot flip score v equals velocity dot y greater than 0. Note, the Boolean assignments in the code above are a common shorthand for programmers. Since we're doing a comprehensive test Boolean and also assigning a Boolean value, we can do both at the same time. Consider this code versus the one-line Boolean assignment above. Yeah. Yeah, that would do it. Play the scene again and check that the animations are correct in each of the directions. F6. Oh, it's like a... that's so weird. Tip, a common mistake here is to type the names of animations wrong. The animation name in the sprite frames panel must match what you type in the code. If you named the animation walk, you must also use the capital W in the code. When you're sure the movement is working correctly, add this line to ready so the player will be hidden when the game starts. Hide. Preparing for collisions. We want player to detect when it's hit by an enemy, but we haven't made any enemies yet. That's okay, because we're going to use Godot's signal functionality to make it work. Add the following at the top of the script if you're using GDScript. Add it after extends area 2D. If you're using C#, add it after public partial class player area 2D. Extends area 2D. Signal hit. This defines a custom signal called hit that we will have our player emit, send out when it collides with an enemy. We will use Area 2D to detect the collision, select the player node, and click the Signals tab next to the Inspector tab to see the list of signals the player can emit. Notice use the Area 2D, select the player node, and click the Signals tab. Signals tab. Next to the Inspector tab to see the list of signals the player can commit. What's the custom? Hit signal there is there as well. Since our enemies are going to be rigid body 2D nodes, we want the body entered body node 2D signal. This signal will be emitted when a body contacts the player. Click connect and the signal window appears. Connect and the connect signal appears. What? Connect where? Oh, connect. Godot will create a function with the exact same connect. There we go. Godot will create a function with that exact name directly in the script for you. You don't need to change the default settings right now. Note the green icon indicating that the signal is connected to this function. This does not mean the function exists, only that the signal will attempt to connect to a function with that name. So double check that the spelling of the function matches exactly. Yeah. Right. I need that one. Body entered, body node 2D. Jesus. Just body entered. Connect. And it should be right. Green icon indicating the signal. Next, add this to the function. Hide. Hit dot emit. $. Collision shape 2D. Dot set. Deferred. Disabled. True. Each time an enemy hits the player, the signal is going to be emitted. We need to disable the player's collision so that we don't trigger the hit signal more than once. Disabling the area's collision shape can cause an error if it happens in the middle of the engine's collision processing. Using set deferred tells Godot to wait to disable the shape until it's safe to do so. The last piece is to add a function we can call to reset the player when starting a new game. Function start position equals pose show $, collision shape 2D dot disabled equals false. With the player working, we'll work on the enemy in the next lesson. Creating the enemy. Now it's time to make the enemies our player will have to dodge. Their behavior will not be very complex. Mobs will spawn randomly at the edges of the screen, choose a random direction, and move in a straight line. We'll create a mob scene, which we can then instance to create any number of independent mobs in the game. Click Scene, New Scene from the top menu at the following nodes. New Scene, rigid body 2D, Control A, Now we need animated sprite 2D. And now we need a collision shape 2D. And visible on screen enabler notifier 2D. Nope, I need it connected to that. Don't forget to set the children so they can't be selected like you did with the player scene. This is done by selecting the parent node. Yes, 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 yes. And that. Control S. Control S. And done. Don't forget to set the children so they can't be selected, blah blah blah. Set the mob node so that it's gravity scale. Mob. Don't forget to set the mob node and set its gravity scale property in the rigid body 2D section in the inspector. Gravity scale 0. Prevent the mob from falling downwards. In addition, under the collision object 2D section, just beneath the rigid body 2D section, expand the collision group and uncheck 1 inside the mask what? In addition, under the collision object 2D, nope, I need to delete you. Wait. Cancel. Control Z. In addition, under the collision object 2D section, just beneath the rigid body 2D, under the collision section, just beneath the rigid body 2D section, expand the collision group and uncheck 1 inside the mask property. Collide with each other. Collision? Where is that? Collision object 2D. What? Property in the rigid body. Oh, collision object 2D. And then collision mask. Okay, there we go. Set up the animated sprite 2D like you did for the player. This time we have 3 animations. Empty new sprite frames. And then need to click on this. This time we have 3 animations: fly, swim, and walk. Fly. Swim. Walk. There are 2 images for each animation in the folder. The animation speed property has been set for each individual animation. Adjust it to 3 for all 3 animations. Animation speed. Fly 3, swim 3, walk 3. Right. Just to 3 for all 3 animations. What? Animation speed. Where is that?
In the place where it is.
Yeah, thank you
Thank you
so much. That
so
means
much. That
all
You're
nothing.
welcome. What would you ever do without me?
I don't know. It's kind of startled when you just came out of nowhere when you've been silent for so long.
Yeah. I'm playing Marvel Rivals. I have my mic muted sometimes to
Fly,
Yeah.
swim, walk. For all 3 animations, you can use the play animation buttons on the left of the animation input field to preview your animations. We'll select one of these animations randomly so that the mob will have some variety. Like the player images, these mob images need to be scaled down. Set the animation sprite 2D scale property. Animated sprite 2Ds. Transform scale 0.75. As in the player scene, add a capsule 2D for the collision. To align the shape with the image, you'll need to set the rotation property to 90 under the transform in the inspector. Alright, collision, object, capsule. Oh, then rotation 90 degrees. There we go. Nope, want it to be one more. Then extend this. Perfect. In the inspector. Save the scene. Control S. Control S. Alright. Add a script to the mob like this. Add a script. Rigid body 2D. Extends rigid body 2D. Now let's look at the rest of the script. In ready, we play the animation and randomly choose one of the 3 animation types. In ready? Yep. Variable. Mob types equals array $, animated sprite 2D, dot sprite frames dot get animation names. Okay. Animated sprite 2D dot animation equals mob types dot
No, it doesn't.
pick. What do you mean it doesn't?
It means it doesn't.
Well, fuck you.
No thanks.
Aw. Okay, first we get the list of animation names from the Sprite 2D's Sprite Frames property. This returns an array containing all 3 animation names: walk, swim, fly. In the 2D script code, we use array.pickRandom method to select one of these animation names at random. Meanwhile, in the C# code, we pick a random number between 0 and 2, select one of these names from the list, array indices start at 0, Finally, we call play to start playing the chosen animation. The last piece is to make the mobs delete themselves when they leave the screen. Connect the screen excited signal to or screen exited signal of the visible on-screen notifier 2D node to the mob and add this code. What? Visible on-screen notifier node visible on-screen screen exited. Connect. Finally, we call to finally we call play to start playing the chosen animation. Excuse me. Q free. Last pieces make mob delete themselves. At this code. QFree is a function that essentially frees or deletes a node at the end of the frame. This completes the mob scene. With the player and enemies ready, in the next part we'll bring them together in a new scene. We'll make enemies spawn randomly around the game board and move forward, turning our project into a playable game. Now it's time to bring everything we did together into a playable game scene. Create a new scene and add a node named main. Reason we are using node instead of node2D is because this node will be the container for handling game logic. It does not require 2D functionality itself. Don't save. Nope. Scene. New scene. Oh, I should probably save this. Just node. Named main. Click the instance button represented. Select your saved player TSCN. Now add the following nodes as children of main and name them as shown. Okay. A timer. Control 3 timers, huh? Let's see. Mob timer. Score timer. Start timer. And then one more. Marker 2D. Great. Start position. Start position. Set the wait time property of each of the timer nodes as follows. Values are in seconds. Mob. No, I just... Okay. Set the wait time. Mob timer. 0.5. Score timer. 1. Start timer.
I'm losing my mind. What's with all these people randomly disconnecting from matches?
I don't know. In addition, set the one-shot property of start timer to on and set position of the start position node transform position to 240, 450. Spawning mobs. The main code will be spawning new mobs, and we want them to appear at a random location on the edge of the screen. Click the main node in the scene dock, then add a child path to D. Okay. Click the main node in the scene dock, then add a child path 2D. Path 2D. Node named mob path. Mob path. When you select path 2D, you will see some new buttons at the top of the editor. At the top of the 2D editor. Yep. Select the middle one, add point. This one, add point. And draw the line path by clicking to add the points at the corners shown. To have the points snap to the grid, make sure you snap grid and use smart snap are both selected. These two. Are both selected. These options can be found to the left of the lock button, appearing as a magnet next to the same dots intersecting lines respectively. Follow the path in clockwise order, or your mobs will spawn pointing outwards instead of inwards. Three, 4. Two, 3, 4, and 5. After placing point 4 in the image, click the Close Curve button and your curve will be complete. Now that the path is defined, add a Path Follow 2D node as a child of Mob Path. And name it Mob Spawn Location. Mob Spawn Location. This node will automatically rotate and follow the path as it moves, so we can use it to select a random position and direction along the path. Scene should look like this. Yep. Add a script to main at the top of the script. Okay. Script time. Main. Add export variable mob scene hacked scene and variable score. Click the main node and you will see the mob scene property in the inspector under main GD. You can assign this property's value in 2 ways. Drag mob tscn from the file system and drag and drop into the mob scene property. Click the down arrow next to empty and choose load. Select mob tscn. What? New scene, save scene, show in file system. Okay. I don't know why. Oh well. That's weird. Here. Next select the instance of the player scene under main node in the scene dock and access the signal dock sidebar. Select the instance of the player scene. Under main node in the scene dock and access the signals dock on the sidebar. You should see a list of the signals for the player node. Find and double click the hit signal in the list. You should see a list of the signals in the list, or right click. This will open the signal connection dialog. We want to make a new function named game over, which will handle what needs to happen when the game ends. Type game over in the receiver method box at the bottom of the signal connection dialog and click connect. Needs to happen. Type game over in the receiver method box at the bottom of the signal connection dialog. What? We want to make a new function named game over. Or right click it and select connect. This will open the signal connection dialog. We want to make a new function named game over, which will handle what needs to happen when the game ends. Type game over in the receiver method. What? Box at the bottom of the signal connection dialog and click connect. Oh, okay. Type game over. Receiver method box at the bottom of the signal connection dialog and click connect. You're aiming to have the hit signal emitted from player and handled in the main script. Add the following code to the new function as well as a new game function. They'll set everything up for a new game. Let's see. Score timer. What? This is the player. Score timer. Stop. $, mob timer. Stop. Function. New game. Score equals 0. Player. Start. Fine. Start. Position. Start timer.start. Now we'll connect the timeout signal of each timer node, start timer, score timer, and mob timer, to the main script. For each of the 3 timers, select the timer in the scene dock, open the signals tab of the node dock, then double-click the timeout signal in the list. This will open a new signal connection dialog. The default settings in the dialog should be fine. So select connect to create a new signal connection. Once all 3 timers have this set up, you should be able to see each timer have a signal connection for their respective timeout signal, showing in green within their respective signal tabs for mob timer, for score timer, for start timer. Now we define each of these timers operate by adding the code below. Notice that start timer will start the other 2 timers, and the score timer will increment the score by 1. Timer function on score timer timeout. Score plus equals 1 on start timer timeout. Mob timer start and score timer dot start. On mob timer timeout, we will create a mob instance, pick a random starting location along the path 2D, and set the mob in motion. The path follow 2D node will automatically rotate as it follows the path, so we will use that to select the mob's direction as well as its position. When we spawn a mob, we'll pick a random value between 150 and 250 for how fast each mob will move. It would be boring if they were all moving at the same speed. Note that a new instance must be added to the scene using add child. Alright, on mob timer timeout. Variable mob equals mob scene dot instantiate. Variable mob spawn location equals mob path slash mob spawn location. Mob spawn location dot progress underscore ratio equals rand function mob dot position equals mob spawn location dot position. Variable direction equals mob spawn location dot rotation plus pi divided by 2. Direction plus equals rand f range negative pi divided by 4 pi divided by 4. Mob dot rotation equals direction. Variable velocity equals vector 2. Rand f underscore range 150.0 to 50.0 0.0. Mob dot linear velocity equals velocity dot rotated direction. velocity, velocity, rotated, direction. What? Velocity. Cleared in the current scope. What? Direction. Oh. Add child mob. Oh my god, I fucked that spelling up so bad. Important. Why pi? In functions requiring angles, Godot uses radians, not degrees. Pi represents half turn in radians, about 3.1415. There's also tau, which is equal to 2 times pi. If you're more comfortable working with degrees, you'll need to use the degree to rad and radian to degree functions to convert between the two. Testing the scene. Let's test the scene to make sure everything is working. Add this new game call to _ready. New game. Let's also assign main as our main scene. The one that runs automatically when the game launches. Press play button and select main when prompted. Oh. F6. What? That access to property or key position on a base object null instance. What? Set another instance as main scene. You can right click main tscn. In the file system doc, select set as main scene. In the file system doc and select main player rigid body. What? Should be able to move the player around, see mobs spawning, and see the player disappear when hit by a mob. When you're sure everything is working, remove the call to new game from ready and replace it with pass. What? Okay, I'll just grab the code. Paste. And grab this. Paste. Oh wait. It's for the ready game. Oh. Game over, new game, copy. Copy. Paste. And then the final function. Paste. Oh, and this one. Okay, maybe it'll run now. What? Player start. Start position. Yeah, just layer. What? 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 Player, is there anything in here that's fucked up? Creating the player. Okay, Control A, delete. Ready. Now. Give me a second. Just a fucking ding-dong ditcher. Maybe? Yes. Okay. Hello, Sneaks.
Hello, Sneak.
Alright. So we grab this.
Yes.
I can hear myself from your microphone super badly.
Yeah, that's because my microphone sucks and picks literally everything up. It's not my fault.
Okay. Function ready. I'm gonna grab that hide function. Process delta. Else, and that position and if. Okay. Hit on body entered. just grab this. And start position. And then rigid body. Extends rigid body. Function Q freeze. Main game. Main. Main. Rerun. What? Oh. Rerun. Crashes again. Position. Valid access to property or key position on a base object or type of null instance. There's this at 12, and then there's something else at 48. No, never mind. What? Player start position. Position. Okay, why? Then is it not working? Activated through. Actually work. The timer need to be activated through function on start timer timeout. Head into the timer node. For the example above, it would be the start timer left side of your screen under the main scene. Change. Invalid call, non-existent function start in base area. If you check the script on your player, you can get this by clicking on the scroll next to your player node on your main scene. You have a start function defined there. Player function. Is this ready? I do not. Function start position. I do have that. I did not. need to be activated through. To do so, I need to head to the timer node. Sample above. But what? Okay, save that. This will save that. Yes, save, why not? Restart. And it still crashes. Invalid acts. 2 errors. Parameter body is never used in the function on body entered. And okay. New game node not found. Start position relative to root main. Connect the. Should see a list of signals. The player node can offer. Function new game. Node not found. Start position. See a list for signals. Find and double click the. Next, select the instance of the player scene. Player scene under main. Node in the scene dock and access the signals dock in the sidebar. Okay. Should see a list of the signals for the player node. Find and double click the hit signal in the list or right click and select connect. This will open a signal connection dialog. We want to make a new click the hit list connect. This will open the signal connection dialog. We want to make a new function named game over, which will handle what needs. Game over. Okay. Node in this under main node in scene dock and access signals dock in the sidebar. You should see a list of the signals for the player node. Find and double click the hit signal in the list. This will open this. We want to make a new function named game over, right? Which will handle what needs to happen when a game ends. Type game over in the receiver method box at the bottom of the signal connection dialog and click connect. You are aiming to have the hit signal emitted from the player and handled in the main script. To have the hit signal emitted from the player. And handled in the main script. Add the following code to the new function as well as a new game function. Hang up for a new game. And what? Oh. And it still crashes. There's one. Start position. Relative. Oh, what is it? Yep, that is. Stop. Hmm. What the hell? What? Oh, I can. Fine, update. What? Um. On the main script, add the following code to the move function. Set everything up for a new game. No, no, what? Um, yeah, player, start position, start timer, start. What? What is wrong here? Should I remove the call to new game? So is it supposed to be in the player code or the main code? Okay, now close. Hmm. Select the instance player scene under main node in the scene dock. Player. It might need to be moved to here. And if it does, run. Base self. Why? Why? The code is exactly the same. Pretty sure. Okay. Main GD. At line 12. New game. Node not found. Start position. Relative to Okay. No, not found. Start timer. Okay. Mm, mob timer. Mob. Okay. All right. Ooh. There we go. Now it's all. Oh. Game over node. Not found. Score timer. Player. Player. And there we go. Oh. All right. There we go. You should be able to move the player around, see the mob spawning, and see the player disappear when hit by a mob. When you're sure everything is working, remove the call to new game from ready. Replace it with pass. Alright, finally. Heads up display. The final piece of our game is a user interface to display things like score, a game over message, and a restart button. Create a new scene, click the other node. Other node. Button and add a canvas layer. Node named HUD. HUD. So you still playing Marvel Rivals then? Stands for heads up display. An informational display that appears as an overlay on top of the game view. The canvas layer node lets us draw our UI elements on a layer above the rest of the game so that the information
Yes.
very fun. So that the information it displays isn't covered up by any game elements like the player or mobs. The HUD needs to display the following information: score, changed by score timer, message, such as game over or get ready, a start button to begin the game. The basic node for UI elements is control. To create our UI, we'll use two types of control nodes, label and button. Create the following as children of the HUD node. No. A. Label. Label. A second label. A button. And a timer. Named score label. Message. Start button. And message timer. Click on the score label and type a number into the text. Field in the inspector. Default font for control nodes is small and doesn't scale well. There's a font included in the game assets called Zelonium Regular TTF. To use this font, do the following. Under Theme, Overrides, under Theme Overrides, Fonts, turn this to new font file, or load. Fonts, Selenium regular, that one. Choose load and okay. The font size is still too small, increase it to 64. Under Theme Overrides. $64. Once you've done this, with the score label, repeat the changes for the message and start button. Message. Theme overrides. Fonts. Load. Font sizes 64. Okay. And start button. Start. Theme overrides. Fonts. Boop. Load. And font sizes 64. Boom. Arrange the nodes as shown. You can drag the nodes to place them manually, or for more precise placement, use anchor presets. Add the text score label. Add the text 0. Set the horizontal alignment to center. Choose the anchor preset center top. Message, add the text dodge the creeps. Dodge creeps. Exclamation mark. Set the horizontal alignment and vertical alignment to center. Set the auto wrap mode to word. Where is that? To word. Under control, layout, transform, set size. Control, layout, transform. Transform. Set size X to 480. Choose the anchor preset center. Start button, add the text start. Start. Under control, layout, and transform, set size.
Oh.
X to 200, and size Y to 100. No balls for you. A little bit more padding between the oh. Okay. A little bit more padding between the border and text. Choose the anchor preset center bottom. Under control, layout transform, set position Y to 580. Okay. On the message timer, set wait time to 2. And set the one-shot property to on. Now add this script to HUD. HUD. Extends canvas layer. Signal. Start game. We now want to display a message temporarily such as get ready, so we add the following code. Functions show. Okay. Function show message text. That's not how you do that. Message text equals text. Message dot show and message timer dot start. We also need to process what happens when the player loses. The code below will show game over for 2 seconds, then return to the title screen, and after a brief pause, show the start button. Function show game over. Show message game over. Wait. Message timer dot timeout. Hashtag, or not hashtag, dollar message dot text equals dodge the creeps. No. Message dot show. Wait. Get tree dot create timer 1.0 dot timeout. Need to get closer in for comfort's sakes for my arms. Start button. Show. Alright, note, when you need to pause for a brief time, an alternative to using a timer node is to use the scene tree's create timer function. This can be very useful to add delays, such as in the above code where we want to wait some time before showing the start button. Add the code below to HUD to update the score. Function update score. Score. Score label. text equals string score. Connect the press signal of start button and the timeout signal of message timer to the HUD node and add the following code to the functions. Alright, press signal of start button. Connect. And timeout signal of message timer. To the HUD node and add the following to the start button pressed. Start button dot label. Wait, label dot hide and start game dot emit. And then for this one, message dot hide. Alright, connecting HUD to main. Now that we're done creating the HUD scene, go back to main instance, the HUD scene in main like you did the player scene. The scene tree should look like this, so make sure you didn't miss anything. Okay. We save all of this. HUD main. And then HUD TSCN. No. Go to main. HUD TSCN. Add it to main. Now we need to connect the HUD functionality to our main script. This requires a few additions to the main scene. In the Signals tab, connect the HUD's start game signal to the new game. HUD's connect the HUD functionality to our main script. This requires a few additions to the main scene. In the Signals tab, connect the HUD start game signal to the new game. Function of the main. By clicking the pick button in the connect signal window and selecting the new game method, or type the new game below in I assume we're still in HUD. Signal. Connect the HUD start games function name by clicking the pick button in the connect a signal window and selecting the new game method, or type new game below receiver method. Okay, in the Signals tab, connect the HUD's start game signal to the new game function of the main node by clicking the pick button in the pick button in the connect signal window and selecting the new game method, or type new game to verify the connection icon now appears next to function new game in the script. HUD. Okay. And in here. Now in here. What? Disconnect. Disconnect. Okay. And now to pick new game. From to the function of the main node. In the new game, update the score display and show the get ready message. HUD update score HUD show message get ready. In game over, right? Wait. In new game, update the score display. Function new game. That's fine. In the script, in new game, update the score display. Show in new game. HUD dot update score HUD dot show message get ready. In game over, we need to call the corresponding HUD function. HUD dot show game over. Finally, add this to on-score timer timeout. To keep the display in sync with the changing score. Right? On-score timer timeout. Yep. HUD dot update score. Score. Now you're ready to play. Click the project button. Wait, what do I do with the on HUD start game? What do I do with on HUD start game? In Signals tab, connect HUD start game to the signal function main code by clicking the pick button in signal window and selecting the new game method. Type new game below receiver method. Verify that the green connection icon now appears. Script in new game update. Okay. Okay. Weird. Say nope. I want to save this, not the website. Start. Shit. Never used in function process. What? What? In new game, main. New game. Update the score display and show the get ready message. Okay, that's right. In game over, where is that? Game over. We need to call the corresponding HUD function. Finally add this to onscore timer timeout to keep the display in sync with the changing score. Remember to remove the call new game from ready if you haven't already, otherwise your game will start automatically. Now you're ready to play. Play until game over and then start a new game right away. The creeps from the previous game may still be on screen. Better if they all... Okay, that's... This is right? Probably. Function, show message. Function, show game over. Function, update score. These two. And that's it. Weird. Crap this. Right there. Mm-hmm. Okay. Okay. And it does nothing. Mm-hmm. Okay, why? Why did it want me to do this? We need to connect the HUD functionality to our main script. This requires a few additions to the main scene. Okay. In the Signals tab, connect... Okay, I'm in main. Connect the HUD start game signal to the new game function. And this should be green connection icon now appears next to the notified that the green connection icon now appears next to function new game. It does not. Yeah, it does not appear there. Why? Why not? Game function of the main code by main node by clicking requires a few additions to the main scene. Main. In the signals tab, connect the HUD's start game signal to the new game function in the main code. Function of the main by clicking the pick button in the connect signal window, selecting the new game method or clicking the pick button in the connect. Pick button in the check a single one out and selecting the new game method below selecting the new game method for the type new game below receiver method in the window. New game. Signals tab, connect the HUD start game signal. Game function. Encode by clicking the pick button in the connect a signal. Oh shit. There we go. What? From Okay, that should work. There we go. And I don't need this. Okay, there we go. Finally. Figured it out. Get ready. And game over. Dodge. What? Why the hell? Get ready. Game over. What the? Dodge the creeps. What the? Okay, in new game. HUD, date score, show message, get ready. Then in this one, HUD, on, okay. This one goes up here. And this one goes over here. Okay. Get ready. And the enemies are coming. Got hit. Dodge creeps. And one more time. Ah, best score that thus far. Cool. Ready to play? Click the play. If you play until game over and then start a new game right away, the creeps from the previous game may still be on the screen. It would be better if they all disappeared at the start of a new game. We just need a way to tell all the mobs to remove themselves. We can do this with the group feature. In the mob scene, it's so weird. What? In the mob scene, select the root node. Select the root node and click the groups. Not groups. Groups tab next to the signals tab and the plus button to open the create new group dialog. Name the group mobs and click OK to add new scene group. Now all the mobs will be in the mobs group. We can then add the following line to the new game function in main. New game. Get tree dot call group mobs q free. The call group function calls the name functions on every node in a group. In this case, we are telling every mob to delete itself. The game's mostly done at this point. In the next and last part, we'll polish it a bit by adding background looping music and some keyboard shortcuts. Finishing up, we have now completed all the functionality of our game. Below are some remaining steps to add a bit more juice to improve the game experience. Feel free to expand the gameplay with your own ideas. Background. The default gray background is not very appealing, so let's change its color. One way to do this is to use a color rect node. Make it the first node under main so that it will be drawn behind the other nodes. Okay. Let's see. Color rect. First node. Color rect node. Be drawn behind the other nodes. Color rect only has one property. Color. Choose a color you like and select layout. A color I like, huh? Red and oh, red. There we go. This one, choose the color you like and select layout. Anchors. What? Layout. Anchors. Anchors preset. Preset full rect. Either in the toolbar at the top of the viewport or in the inspector set that it covers the screen. You could also add a background image if you have one by using a texture rec node instead. Sound effect. Sound and music can be the single most effective way to add appeal to the game experience. In your game's art folder, you have two sound files, housed in a forest loop.ogg for background music and gameover.wav for when the player loses. Add the audio stream player nodes as children of main. Add two audio stream player and audio stream player 2. Name one of them music and the other death sound. Music. Death sound. On each one, click the stream property, select load. Load. Art. Music open. And same for this one. Load art gameover.wav. And click load and choose the corresponding audio file. All audio is automatically imported with the loop setting disabled. If you want the music to loop seamlessly, click on the stream file arrow, select this one. Click the stream file arrow, select file arrow, select make unique, and click on the stream file and check the loop box. What? Oh, loop. To play the music, add in the new game function. Add music dot play. Add music dot stop and the game over. Music dot stop. Finally, add death sound play in the game over function. death sound lay. Alright. Keyboard shortcut. Since the game is played with keyboard controls, it would be convenient if we could also start the game by pressing a key on the keyboard. We can do this with the shortcut property of the button node. In a previous lesson, we created 4 input actions to move the character. We will create a similar input action to map to the start button. Select project settings, project settings, add, enter, no, not enter, start game, okay. Now would be a good time to add the controller support if you have one available. Attach or pair your controller, and then under each input action that you wish to add controller support for, click the plus button and press the corresponding button, D-pad, or stick direction that you want to map the respective input action. In the HUD scene, select the start button and find its shortcut property in the inspector. Create a new shortcut resource by clicking within the box. What in the HUD scene? Oh. HUD. Select the start button. Scene, select the start button and find its shortcut. What? Oh, okay. And shortcut property in the inspector. Shortcut. Mode? No. New shortcut. Create new shortcut. Okay, new shortcut. Resource by clicking within the box, open the events array, and add a new array element to it. By clicking on the array input size, create a new input event action. No, not that. New input event. New input event action. And select start game action. What? Let's pull this out a bit more. Action. Start game. Now when the start button appears, you can either and with that, you completed your first 2D game in Godot. Run it. Oh, that's some interesting music. Aw. Okay, enter does work. Near the edge of success means death. Okay. that. First game, yeah, finishing game with others. First 3D game. We actually don't need to go over this. We're fine skipping it. Alright. Let's see, how long have we been streaming for? 5 hours? Okay, I think here's a good place to stop. Ugh. Yay, learning Godot, episode 1. Huzzah. Yay. Alright.